Good morning, everyone. Thank you for being online. Welcome to our Zoom session for the Photonics Power and RF Packaging Forum 2022. This is the second edition, and it's co-organized by the CITC and Yole Group. I'm Emily. I'm Director of the Division Semiconductor Memory Computing at Yole Intelligence, part of Yole Group. And I'm co-hosted this session with Marco Koelink from CITC. I will let you introduce yourself, Marco.
Good morning, everybody. My name is Marco Koelink. I'm the Business Development Manager of CITC.
Thank you again for being online. So we are our host and we will guide you through the event. So there will be 3 sessions today. One on photonics packaging, the second one on RF packaging session, and the third one is on power. Before we start, there is something we need to tell you that's related to the Q&A. So Q&A box is available for your questions. So that's at the bottom of your Zoom. And do not hesitate to ask questions during the presentations or even after if you wish. We will make sure that you get answer afterwards. If any issues, you can chat with us and we will help. So that forum is recorded and you will be able to receive and rewatch that webinar in a couple of days. Another important thing is the program of the day. As we said, there will be an RF packaging session only with 2 people because unfortunately Jérôme Serrand from JSR cannot make it. So be aware that we will restart the RF packaging session at 2 p.m. instead of 1:30. I think now we can proceed. And once again, if you have any issue with the platform or with the questions, feel free to chat with us or send us an email. I think we can start. So to start that webinar, I would like to give you a short introduction on Yole Group. So we are a French market research company, and now we have grown into, let's say, a larger group. There are 3 main entities. Yole Intelligence, that is focused on market technology and strategy consulting. So we are publishing reports in which we discuss semiconductor trends and all the leading application trends in electronics. We are also, let's say, doing some consultancy on M&A and companies evaluations. We have a sister company named Yole System Plus, based in Nantes, who is working on technology, process, and cost analysis. Some of you may have seen some teardowns and reverse engineering. So please feel free to reach out to us if you need any comparison analysis. And we have a third sister company named Piseo, who is focused on doing characterization of electro-optical performances, a lot of photonics devices, and they are specialized in design and industrializations of systems. What we do actually, we have been in the field of the semiconductor industry for 25 years. We are participating to more than 120 annual conferences. We are doing interview more than 5,000 per year. We have a lot of product teardown tracks available, more than 1,250. That's how actually we get to know exactly which type of component are used. And we have more than 100 analysts who are based worldwide to support that market research and analysis. A bit more on how Yole Intelligence is organized. So we are specialized by thematics. I'm part of the SMC where we cover semiconductor packaging, semiconductor manufacturing, memory, computing and software that includes processors and artificial intelligence. Some of my colleagues who help us for the photonics side are specialized in photonics, lighting, imaging, sensing, actuators, and also display and microLED. We have a team with us today who is specialized on radio frequency, compound, power electronics, and they are working also conjointly with us on RF and power packaging. And we have a team who is dedicated to emerging technologies and old electronic systems. So before starting the webinars and all the good presentations that were prepared for today, I wanted to share with you some highlights on why we decided with the CITC to focus on photonics, RF, and power. That's 3 fields in packaging where we still see a lot of innovation, needs of, let's say, R&D and new materials coming. So the first one will be dedicated to silicon photonics. Here you can see 2 schemes of evolutions of the package that we have seen, let's say, the evolution over the years. So once we have 2.5D packaging, where we are using an interposer for adding components of memory, logic, sometimes MEMS, and RF components. So those type of interconnects are using bump and through silicon vias. And the ultimate goal is to have a real 3D integrations of those components when they would be stacked onto each other. Next slide, please. Here, conjointly with our colleagues who are covering the silicon photonics, we have went through the different type of designs that you see. So the whole questions is to know how we could integrate with a good form factor and let's say good performance, the optical fiber. So here you have a diversity of integration that you will receive in the presentation of our speakers, where you see optical fibers or directly attached to the PIC, or some of people are working on stacking the EIC on the PIC that is wire bonded to a PCB. So depending on, let's say, the type of die and the performance we are looking for, we have now in our toolbox a diverse portfolio of, let's say, of package platforms. Thank you. For the next slide. So that slide is about, let's say, the 5G packaging roadmap that we see in Yole. So when we look at the evolution over the last, let's say, 20-25 years, related to the location of the antenna and the needed for the RF components, the evolution of the package had been tremendously high in terms of reduction, decrease of the thickness, and into the performances. So the transition from 2G to 5G has, let's say, pushed the designer to place the antenna in different places, from the outside phone body that we remember well, to the introduction into the phone case. Then that was moved on the flex PCB, then in the package. Now people are working at direct integration at the wafer, let's say, wafer stage. We will rediscuss that with my colleague Gabriela later in the day. Next slide, please. And that last slide is more for our power packaging session later in this afternoon, where our colleagues still see a lot of, let's say, challenges coming, big for the wideband gap, and also for all, let's say, the emerging devices. So whether we look at the application, if it's for industrial, for rail, for PV, all are looking for better performance, better form factor. And when looking at the system, the challenges and the constraints that they have in terms of design are related to power density, the temperature of operations, let's say, the form of the cooling systems, and all these constraints have an impact on the type of packaged. So for power device, whether it is a MOSFET, an IGBT, or a GaN HAMT, every design requires, let's say, improvement in materials and improvement in the way we embed. So later in the day, there will be a presentation where we talk about embedded package as well for R&D, but also how we put that into a commercial product. So if we look at the next slide, please. I was saying that we need innovation in terms of materials. Here, that's, let's say, the summary of all types of interconnections that we have in the package and external to the package, where you have your die on a substrate on a base plate and the thermal interface material that we know that have been under research for many years. That's a good summary of all, let's say, the level of the level of innovation that we can work on to better improve the power and the thermal management of the package. And my next slide, actually my last slide, was also to share with you, let's say, the diversity of package, where people have transitioned from, let's say, the traditional power module package to something, let's say, more efficient in terms of thermal management and also form factor. So we will discuss that today. Here you have, let's say, the single power module, and I would move towards the left, towards the embedded package, where the players are providing something very efficient in terms of heat dissipation, and the fact that they embed the die into the PCB make it very very easy to integrate into the system. So now the stage, I will give the stage to Marco, who will present the CITC and their activities. Thank you, Marco.
Thank you, Emily. Can you see my screen?
Yes.
So good morning. For those of you who just dialed in, my name is Marco Koelink. I'm the Business Development Manager of the Chip Integration Technology Center, or CITC. I will briefly like to introduce you to our organization. CITC is a joint innovation research center in the field of integration and packaging for semicon and photonic applications. We were founded in 2019 in close collaboration with TNO, that's the National Dutch Research Organization for Applied Sciences, and the Technical University of Delft. We are located on the Noviotech campus in Nijmegen. That's the previous area of Philips Semiconductors in the Netherlands. And that's not coincidental, because also companies like NXP and Amplion and Nexperia are located on this site, who are also our initial customers with whom we started this activity. So why did we start this activity? Integration and packaging technology is of growing importance. It actually goes from, let's say, a passive encapsulation to an active part of the device for many applications. And in the Netherlands, there was voiced a clear wish from the industry that they had a need for an organization to co-develop these technologies. What do? We provide access to companies and organizations to innovation, infrastructure, and education. I'll get back to that in a little bit more detail later. The current main application areas are not incidental: power, RF, and photonic integration, which are the topics which you might recognize in our forum today. And in principle, we develop packaging solutions and we validate new technologies through functional proof of concepts and prototypes. This slide shows some of the partners that we work with. Typically, we identify research topics in collaboration with IDMs, with device manufacturers or system providers. And then around these topics, we like to bring in material suppliers and equipment suppliers as well, so that we in principle create an ecosystem in which we have the opportunity to optimize our technical solutions within the triangle of design, materials, and processes. Getting back to our offering, so our main offer obviously is access to innovation. We run different research programs in collaboration with customers and partners, in which we work with device manufacturers, equipment manufacturers, and IDMers, like I explained. In order to support those activities, we have created an extensive assembly laboratory in Nijmegen, but we use that facility also in addition to supporting the innovation programs to support and contribute to our education offering. Our lab serves as a demo and application lab for new equipment and materials. And we also allow researchers into our lab from other organizations as, let's say, as a guest researcher. Finally, we also have a close collaboration with several organizations in the field of education. So we provide access to education. We think that's important because know-how and experience in Europe in the field of packaging is scarce nowadays. And if you want to, let's say, reshore packaging activities to Europe, start new activities in Europe in this field, in addition to the resources, you definitely also need the manpower. So that is a very important part of our proposition, that we, in addition to allowing students in our facility to do internships, graduation programs, PhDs, postdocs, we also have a close collaboration with academia to provide real education in the form of minors in the field of packaging. A very brief introduction in the 4 programs, 4 topics that I already mentioned. So we have an activity going on in power or thermal high performance. We have a program in the field of RF and millimeter wave package development. We have a topic called digital manufacturing, which is a little bit supporting towards these other 3 topics. And last but not least, we are active in the field of photonics. And I very briefly would like to show you what kind of research we are doing in these individual areas. So for power, we are active in the field of high thermal performance for discrete components. So in the chart that Emily showed, it's a little bit on the left side. We are working extensively on silver sintering, but specifically pressure-less sintering. Pressurized sintering is a technology which is meanwhile quite mainstream in the field of automotive power for electrical vehicles, but it's almost exclusively utilized on ceramic substrates. And that combination works very well. However, if you would like to apply silver sintering on discrete components who are typically using copper lead frames, you'll find that the reliability of these solutions is typically not so good. And it has very much to do with the mismatch of the CTE, so the thermal expansion of the copper substrate compared to the rest of the system. So one of our goals in this program is to optimize the design and the materials and the processes to achieve a reliable solution for these discrete kind of components. And in order to do that, we use extensively simulation technologies and advanced characterization to pretty much enable predictive failure behavior of these kind of systems or devices. Just to give you a little bit of an overview of the kind of process control and inspection that we do. So we have optical inspection to make sure that the die is planar. We have confocal microscopy to identify the non-planarity, X-ray microscopy to identify voids. We do cold and hot die shear to enable the die shear strength and the cohesion and adhesion of the different layers in the package. CSUM is a very important tool where we try to identify delamination. And last but not least, we also extensively make cross sections of devices that have failed, or from devices from whom we suspect they will fail, to in order to identify location of failures, which kind of failures, and also the progress of failures in time. The RF chip packaging program focuses on RF solutions for 6G and second generation automotive radar application. So typically a frequency range between 100 and 150 gigahertz. We focus mainly on two specific topics. The first is the design and realization of efficient and suitable antenna and package solutions on top of the RF package. And secondly, one of the other great challenges in these kind of applications is the design and the manufacturing of a suitable redistribution layer in between the chip and the antenna solution, focusing on the right materials with corresponding good and efficient RF dielectrical parameters. We focus on the necessary resolution of these structures, in particular also the vertical interconnects and the surface roughness that is required for these high frequencies to make sure that you minimize radiative loss, especially in these redistribution layers. The third topic is additive manufacturing. It's a topic which is closely linked to, let's say, advanced packaging in general. In collaboration with the TNO Hol Center in Eindhoven, we are also now making the transition from, let's say, more traditional or classical packaging technologies to more advanced packaging technologies that also utilize front-end technologies, let's say lithographical technologies. Eindhoven Hol Center has a long history both in the development of printed and flexible electronics on one side and display technology on the other side. Both technologies, both developments are meanwhile relatively mature, so they are at present looking at new challenges and new opportunities to continue research utilizing these capabilities. And we think that advanced packaging is a very suitable topic for this facility, in particular because the additive manufacturing capabilities that TNO Hols has developed over the course of the last 10-15 years are an excellent complement to their advanced packaging capabilities using more lithographical technologies. If you look at the packaging world right now, there's an increasing interest in additive capabilities. In general, the semiconductor industry is rather conservative in adapting new capabilities, new technologies, and new processes. But additive manufacturing is meanwhile becoming so mature that it really provides very interesting and also economical, feasible alternatives to front-end technologies who are in general very expensive. So additive manufacturing is an economical, interesting alternative, but it's also technically increasingly providing technologies that can not only replace, but also improve and complement existing packaging technologies. Last but not least, very briefly, something on our activities in the field of photonic packaging. So one of the largest challenges in photonic packaging is to get to low-cost, high-volume production capabilities. In photonic packaging, the cost of packaging easily amounts to 80 or 90% of the total cost of the optical device. So it's a very important challenge to get these costs down, in addition to being able to produce larger volumes of products to enable photonic packaging to, let's say, come to fruition and really reach its potential in the market. To that extent, we are working with an equipment manufacturer to make manufacturing equipment more mature and faster, going from an R&D equipment via semi-automatic eventually to full automatic equipment. So that's a company called Etteplan in the Netherlands with whom we are collaborating there. We are investigating potential technologies where we can go from individual product assembly, for instance, to strip level assembly. You can see in the picture on the screen an example of a plastic package that we are developing together with RGR Technologies to replace the more well-known gold-plated butterfly packages in photonics. And if you go from an individual package to strip level assembly, you can improve the speed of assembly because you can do certain processes in parallel. And the top picture actually is still a computer animated picture, but in the bottom left you actually see a picture of a real prototype. So that's an activity which is really very close to being realized. And last but not least, on the right hand side, you see a picture that describes some of the ideas that we are having to move from active assembly to passive assembly in order to eliminate active assembly as much as possible, because it's a very time consuming and very expensive technology. And there are three things that we are working on. First and most importantly probably is the move to go to pluggable optics. So if you are building a photonic assembly, the fiber connection very often makes it very difficult to utilize existing production capabilities from the semiconductor industry, because the fiber typically gets in the way. And if you can eliminate the fiber connection to be added to the assembly at the very last point in time, you can then actually utilize existing low-cost, high-volume semiconductor manufacturing technologies to build the optical assembly, and then in the end, through pluggable optics, make the optical connection. We think we can do that by utilizing a PCB platform that entails both electrical and optical guiding structures. So that, those are the red stripes that you can see on the assembly substrate over there. And a third topic that we want to start working on is to flip chip the optical chip to this substrate to enable high density electrical interconnect by moving the electrical connections from the top side of the optical die to the back side, so that you can also eliminate wire bonding connections and go to stud bumping or other bumping technologies, which you can make in much higher numbers. So you can get a higher density, and you also enable a much better RF connection, for instance. So in summary, CITC, a one-stop shop for all the steps of package development for photonic and semiconductor applications, with focus on power, RF and photonics. And core capabilities that we focus on is material characterization, evaluation and benchmarking, technology and process development, specifically for assembly and integration. We design and fabricate functional proof of concept packages and prototypes. And finally, we validate technologies and processes and package concepts that eventually can also be transferred to production. So in that sense, we try to gap the bridge between academic resources, academic institutes, and real industrial assembly processes at OSATs and other assembly organizations. Thank you very much.
Thank you, Marco, for that presentation of CITC activity. I think it's now time to open the first session that is dedicated to the photonics packaging. So that will there will be two parts of that session. We have many speakers on this topic. So the first part will be we will welcome Peter, who will be our moderator today. Peter Hamsma. I will let you. Good morning, Peter. And so we have 3 speakers in that session. Sorry, and make sure that the slide is displayed. So our first speaker will be Padraig Morisset, who is Pilot Line Program Manager from the Tyndall National Institute. He will talk on photonics packaging of PICs from research to pilot scale manufacturing. Our second speaker will be Martin Schell, who is Executive Director at the Fraunhofer Heinrich Hertz Institute. Martin will talk about hybrid photonic integration for communication, quantum, and sensing. And the last speaker of the first part will be Andrew Robertson, who is CTO of Photonics, and Andrew will speak about quantum enabling photonic packaging. Once again, if you have any issues, please feel free to use the Q&A chat to ask any questions.
So our next speaker is Martin Schell. He is Executive Director of the Fraunhofer Heinrich Hertz Institute in Germany. He is also a professor at the Technical University of Berlin and has also considerable industrial background from, amongst others, Infineon. So he will talk about the hybrid photonic integration for communication, quantum, and sensing. And as I understand, he will explain a lot about the HHI's polyboard concept. Professor Schell, the floor is yours.
Thank you very much for the introduction and giving me the chance to introduce our technologies here. Let me start with 2 pages about Fraunhofer HHI overall. We are around 500 people with a 70 million budget, and we have 3 large areas of research. One is video compression. H.265 is the latest codec here. So if anybody in the world buys a cell phone, a single-digit fraction of a cent goes to us for our contributions to the codecs patent pool there. Another third is the photonic and the wireless networks. Here in the photonic park, we focus on very short scale communications, like communications in an electromagnetically different environment like shop floors between machines. Last one is about 1/3 of HHI, and that's the focus of this talk, is the photonic components. Here we work up to 145 gigahertz speed. We do communication components, of course, terahertz sensing, and also activities for quantum key distribution. Within photonic components, we have our longest experience with indium phosphide chips. We go up to 100 gigabit lasers, high bandwidth detectors, and single photon detectors. The photonic integrated circuits started in the 2010s with monolithic indium phosphide, and we have added in the hybrid polymers, and in the last years also minor activities on silicon nitride and thin film lithium niobate on isolator. We have production capabilities for pre-series and small volumes. And just to make the contrast to the last talk, we typically work with techniques which result in low single-digit assembly times per year per device. And if you have in mind that a year has 500,000 minutes, then you add up with a single line capacity between 100,000 and 300,000. And this is unfortunately in fiber optic segment, in today's application segments, that's enough for many of the applications there. So just to clarify the integration technologies, I added this slide. So we talk about monolithic integration when all functions are realized in a single material system. This is very well developed for indium phosphide, where you can integrate all laser detectors, modulators, and waveguides. Second technology you find in the research and in products is heterogeneous integration. This kind of a combination of passive active materials on wafer level, like indium phosphide on silicon, which are available since a couple of quarters in foundry services on the market. There's also lots of new research activities with new materials like BTO, polymers, or plasmonics. Focus of this talk is going to be hybrid integration. That means that passives and actives are combined in a device level with pick and place technologies. And I'm going to show in the later some tunable lasers in different combinations on passive materials like silicon nitride and active materials like indium phosphide and polymers. The big advantage of hybrid integration is that it allows to choose the best material for each optical purpose. There's unfortunately in optics, there's no one size fits all like in electronics silicon is. And I'm also trying to show that the additional assembly efforts can be managed. This is a short introduction of our polymer hybrid integration platform, which we call Polyboard. We use a Polyboard as a purely passive waveguide platform with single mode waveguides. We can adjust for refractive indices between 5 per mil and 30 per mil. The good thing is due to its index matching and its mechanical index matching with glass fibers and index matching with glass, we do not need any polishing, any end phase treatment process. One of the first examples we realized with this platform was a tunable laser. For the non-photonics people in the call, this is about a 3 millimeter device. The gain chip here has high reflection on the left side. The indium phosphide is butt coupled here to the polymer. The second reflector, which you need in a laser, is here under the waveguide. It's a tunable Bragg grating where you can tune the wavelengths by heating the stripe here and changing the period of the wavelengths just by temperature. And you can see that we can tune between 15 and 20 nanometer with such a simple device. 1550 is a wavelength of choice for telecom activities. We have 2 years ago also started to use other gain chips like for 1064 nanometer and for 785 nanometer, because in that wavelength range there's no or nearly no communications applications, but for sensing these wavelengths are more interesting than the typical telecom band. Another technology which the Polyboard is quite unique in is these thin film filters, which can be inserted into slots into the waveguide. And if you have a thin film filter with 2 layers in the simple case and up to 10 or 20 layers in the complex case, you can manipulate either polarization of the optical waveguide or of the optical wave, or you can split wavelengths so that one wavelength is passed through and the other wavelengths are reflected. That's a very important capability within fiber optics communications and also in a lot of sensing applications. The filters we insert are manufactured on a 4-inch wafer scale. One of these wafers has around 10,000 pieces, which makes this process very volume capable. On the right-hand side, you see these very tiny filters which result from these wafers, and they then are inserted into the Polyboard slots. This is one example from a Berlin company using this technology for some optics component in network quality diagnostics. Another thing we realize, and Patrick mentioned that attachment of the fiber is a very complex thing, or it's a very time-consuming thing in manufacturing photonic components. If you have 2x2 or 5x5 millimeter components, it's very easy to bring them from one machine to the other. You have a horde of 100 or 500 pieces. Whenever you attach 1 meter of fiber, everything gets much more complicated. So the target here is, as my predecessor mentioned, to attach the fiber in the very last process step and to do it as easy as possible. So what we're doing here is etching new grooves in the polymer. And contrary to solid state materials like silicon, polymer has some elasticity, so it exercises some pressure, so that's a simple click in process, and the required accuracy of 0.1 to 0.2 micrometer is just guaranteed by lithographic measurements. So it's an alignment-free process, and it's just at the very end, it's fixed by an additional drop of glue. Another advantage of this technology is that you are not bound to any crystal axis. You can make these U-grooves in any direction you want. Based on these U-grooves, which were used for fiber coupling at the very end of an optical component, we also started to implement these U-grooves in the middle of a photonic integrated circuits. And so that opens up the possibility to integrate some free space region in the middle of some photonic integrated circuits. And that opens up a huge amount of additional possibilities because you can now put into your optical waveguides each and every other material into which the optical functionalities you are interested. And I'm going to show you some examples about how these alignment processes go. That's a pickup of the polyboard. We do that automated for medium volumes, depending on the glue. Pick up the fiber. Just simply press it in. Then the active alignment of the chip. So contrary to my predecessor, I'm pretty convinced that the additional 20 to 30 seconds of the active alignment process do not destroy many of the cost calculations. And at the very end, you have such a nice device. So we have not optimized for speed because we are research institutes, and I'm pretty confident that whenever you do that optimized for speed, you end up with some 2 to 3 minutes cycle time per device maximum. And that's within the budget of a large amount of components. Of applications. Coming back to the U-grooves and the free space room in between, the first thing about photonics people is when they have access to these free space things is to put an isolator in between. Each laser, or nearly all lasers with high quality, should have an isolator inside, which protects the laser from back reflections from the optical system, or whenever the connector here is not perfect, you get some minus 10 dB back reflection or so, which destroys coherence, has a potential to destroy coherence properties for the laser. And here on the lower hand, you see the subassembly. It's about 5 to 6 millimeters long. You see the DFB laser, which I introduced a couple of slides before, going through a waveguide, going through the isolator, and being fed into a single mode optical fiber at the very end. And the additional loss introduced by the isolator is of the order of 1 dB. So this is on a single device level. If you go to very high levels, very high data consumptions, you want to have arrays of these devices. And one example where we do that is in the European project named Terrific, which is targeting 800 gigabit per second and higher transceivers. A general picture of these functionalities is shown here. You have here your arrays of lasers. Here, your arrays of photon detectors. These nice looking waveguide arrays here are so-called AWGs, arrayed waveguide gradients, they do the spectral filtering so that you can combine 8 different wavelengths here into one single output fiber, or take the 8 input wavelengths here going into the system and separate them to 8 different photodetectors. So that as a result, you can get 8 times data transmission capability. So the one thing which is please keep in mind that we talk here about 50 gigabaud frequency. That means the high frequency properties are a bit more demanding when, compared to normal microprocessor speeds. And what is important here also is the connections between the drivers and the which are typically in silicon or BiCMOS, and the optical element, be it a laser or a photodetector. And these 8 times parallel 50 gigabaud lines is a non-trivial thing. And we use our so that's a bit oversimplified. At the very end, you end up with a connection, with an electrical connection with, between the 2 driver arrays and one of the laser arrays up here, which is more complicated because for some detailed technologies, you also want to adjust a couple of 100 microns height difference. And these flexible interconnection components you can also use design and manufacturing using the polyboard technology. This is basically polyboard without optical functionality, but this high-speed coplanar strip lines integrated. And that works up to 100 gigahertz 3dB bandwidth. And we are pretty sure that this is something going to be used in the future more and more. The last thing I want to show you in that multiple co-integration segment is this terahertz transceiver. It would be too much to go into each and every detail of what that thing does. It falls into the category of microwave photonics. So here you use the photonic integrated capabilities to introduce electrical functions like true time delay or like frequency filtering, which are at microwave frequencies of 10 to 50 gigahertz, which are very difficult to realize. So in microwave photonics, you put the microwave signal onto an optical carrier. Then you do all these optical functionalities in a photonic integrated circuits. So, and at the very end, you convert the photonic signal into detectors again. So this is the functionalities we integrate together with our partners in this European project. The polyboard here in the middle is for doing these waveguide, all these manipulations. The indium phosphide integrated chips here are the light sources and terahertz transmitters. And there's also some silicon nitride photonic integrated circuits, integrated but coupled because the rings which you use for resonating have higher quality in silicon nitride than in polymer waveguide platform. The upper left then is the output, and the fiber array is just for diagnostics. So at the very end, this is an electrical signal in and electrical signal out device, where all the manipulation of the electrical signal is done in photonics domain, but the user sees this as a purely electrical in and electrical out device. I mentioned quantum technologies, and in quantum technologies, coming to the last part of my talk, we use these U-grooves to a very large extent. The quantum people, they are not integrated, not interested into isolators functions. They want to have nonlinear functionalities inside an optical photonic integrated circuits. So these nonlinear optics is used for generation of photon pairs. You put one 770 million nanometer, 11550 nanometer photon in, and you get out 2 photons at half the wavelength. Sorry, the other way around. So you put on one high energy photon in, get 2 low energy out, or you put 2 low energy in, get 1 energy out. If you generate photon pairs with that, they are entangled, which is necessary for some formats of quantum key distribution and for quantum computing. In this case here, we use a second harmonic generation as a first proof of concept, and you can see that you get with a very easy available 1550 nanometers, you can, and very easy controllable with telecom technologies, we can play around with phase and with wavelengths and with intensity modulation up to 100 gigahertz. It's very easy at 1550, and with this second harmonic generation, we can transform these capabilities into other wavelength ranges, which are both interesting for sensing applications and for quantum communications. Another example of that is putting a periodically poled lithium niobate here. And that's, again, the generation of a photon pair. You have a high energy photon here, which in this nonlinear process is split into 2 entangled photons. You use 1 photon at 1550 nanometer to do your quantum communication. And the other photon, for example, you can use for heralding. Heralding means telling the receiver that there's a certain time slot where the receiver should be sensitive for the single photon arriving on the other channel. This is very helpful in reducing the noise on the receiver side, because you can switch off the detector for a large share of the time windows. What is a big challenge here is the isolation. So you have very high input power here, and you don't want to have any crosstalk, any remainder of the pump light in your single channels. The order of magnitude of isolations you require here are 40 to 50 dB. And this is our filter technology. This is much easier to be solved in a polymer platform than compared to silicon or silicon nitride platform. Other example of this photonic quantum technology is very simple, just a different crystal, and jump over that. And the last thing from quantum technology I want to show is the NV centers in diamond. NV centers in diamond are a quantum molecule, quantum element, which has quantum state also at room temperature. That makes them very attractive for applications. These NV centers are very sensitive to magnetic field, so they are supposed to, or they compete with today existing squids, which require single-digit Kelvin cooling. NV centers target in reaching the same sensitivity for magnetic field without these Kelvin temperature requirements. We use our polypore technologies to address multiple inputs and output to address 9 different of these NV centers in diamond. We believe that this is scalable and that you can, by that, introduce specially solved magnetic field sensors. They are used, for example, in medicine to get a diagnostic of the activities in the brain, which can be identified by magnetic fields. So to come to a conclusion, I've showed you some examples of hybrid integration. I do believe that hybrid integration is, at least for a couple of 100,000 pieces volumes per year, is a technology's choice, because it allows for choosing the best material for each optical purpose. Shown you some pictures of automated assembly. And the wide wavelength range allowed for by the polyboard technologies is very helpful for communication and non-communication apartment. As an example, I showed some 800 and 1.6 terabit per second transceiver and some quantum optics. Thank you very much.
Well, thank you very much for your great presentation and your introduction to all the great technology that you can offer. There's some opportunity to ask questions via the chat. I don't see any questions at the moment in the chat, only a compliment. Maybe I can ask a small question myself. I can imagine that among the participants are people who would really like to use your technology in their products, so really go to commercial applications. So do you have any contacts with higher volume manufacturers, and how does it work with IP? How can people get their hands on your technology?
So it's a wafer technology. So depending on the size, on our 4-inch or 6-inch wafer, there's a couple of thousand pieces. Whenever we are able to supply these volumes in up to a couple of wafers per month or something like that, if the customer is interested in that. If the customer wants to scale up, he has to transfer the process to an own fab. This is polymer. If you compare the polymer manufacturing processes with the silicon or indium phosphide processes, I would estimate that's a factor of 10 less expensive and easier. So that should be not too much of a problem. There's one Korean company using these polymer processes in their own fab. So I'm guessing that 50% of the Korean 5G network in their backbone has some polymer circuits inside. That's so that the Telcordia qualification has been done for some products. The good thing is you have to think about the transfer only then when the proof of success of your product has been done by sampling to the customers. And for the initial production, we can supply. For later production, whenever it takes more than 20% or so of our capacity, you should think about your own production.
Yeah, all right. I still don't see any other questions in the chat. Maybe I can ask a second question. I'm not sure if it's a smart question, maybe not. But I think you explained that the waveguides in your polyboard technology are fiber matched. So I guess also your game block is fiber matched. Would it be possible to put your game blocks, let's say, on top of or embedded in the chip rather than at the edge?
There's a huge discussion in photonics community. What is the best way to make coupling between optical materials? So what we do is butt coupling, right, at the edge. And there's also waveguide coupling where you either use grating couplers or some other methods to transfer the light laterally down from one waveguide to the other. We are big fans of butt coupling simply because we believe that the insertion loss is lower than in the other technologies. And the big advantage of this top-down approach is that it's wafer scalable in one of the processes, like microstamping or whatever. In the volumes which are real in communication industry per today, I believe this is not yet needed. But the quality of the coupling, if you talk, you have the coupling inside the laser cavity, right, in these examples. And the coupling loss inside the laser quality reduces the quality of the laser in terms of line width in terms of noise properties. The coupling loss outside the laser is not so important because you can simply drive your laser a bit harder. So we're trying to make highest quality lasers, so we have to use the lowest insertion loss, and that's why we end up with butt coupling and with active alignment.
Yep, clear. Okay, thank you. Yeah, I don't see still any other questions in the chat. If you have still questions, please put them. Maybe Martin Schell is able to answer them after all. Then I propose that we continue with the next speaker. And our next speaker is Andrew Robertson. He is currently the Chief Technology Officer at Bay Photonics, and he will talk about quantum enabling photonic packaging, where he will explain that quantum photonics typically has requirements quite different from regular applications, and also occasionally require low temperature operation. And he will explain how Bay Photonics can help in that field. So please, Andrew Robertson, the floor is yours. Go ahead.
Thank you, Peter. Can you see my full screen?
Yeah, we see it perfectly.
Okay, thank you. Well, thank you for the invite, and good morning to everybody. I'm Andrew Robertson from Bay Photonics, and as was said, I'll talk a little bit about the quantum aspects. I'll give an introduction to Bay Photonics, who we are. I'll touch on why does quantum matter, and some of the applications, and as I go through the presentation, I will point out some of the applications, because I'm usually either speaking to people who don't think quantum is going to be here until 20 years into the future, or I'm talking about people who want to invest a lot of money in it because it's here now. So it's somewhere in between there. So I'll talk about quantum photonic integrated circuits, where we are, and in terms of real applications and real products. Some of the problems involved with quantum, which if you have been involved in photonic packaging for as long as I have, and as long as some of the speakers have been in this session already, it is a difficult task. When you then think of quantum photonics, there are some additional issues that you have to worry about. And then I'll touch on some of the future enabling technologies that will hopefully solve some of those issues that there are with quantum. So who are Bay Photonics? Well, we are an independent packaging house, photonic packaging house, and we do downstream photonic packaging processing. So that's anything from the chip level. So after the wafers have been diced and any coatings, annealing or whatever, we will take the chip and we will then undertake the processes: die attach, wire bond, packaging, co-packaging, hermetic, and we will put the devices in any package we can feel is appropriate. We'll also do optical and electronic design and simulation, and look at the thermal issues, which has been touched upon. People have mentioned cryogenic, and that is one of the things, one of the aspects of quantum PICs that is different from other photonic devices. So that's becoming more important. And we will also develop a manufacturing process. In the quantum world, we're usually dealing with people who have spent a long time developing a PIC, and a long time waiting for a multi-project wafer run. And then at the last minute, they think of packaging. And as Patrick mentioned earlier, it's best to think of these things up front. But this does not often happen, certainly in these new technologies. We were founded in 2007, and we comprise of mostly engineers from large telecoms, former large telecoms companies, Nortel Networks and JDS Uniphase. And all our engineering team has many decades of industrial experience in photonic packaging. So where are we? Well, Bay Photonics, we are not anywhere near San Francisco, which often people think, because we're called Bay Photonics. We are in fact in Torbay, which is the south, not the Wild West of England, but the southwest of England on the coast in between Exeter and Plymouth. And the reason we're here is because of the heritage of photonics and photonic packaging here. The picture on the upper left shows what was STC, which became Nortel, their factory, which was built here in the 50s. And it was from there that the first undersea cable photonic fiber optic components were actually built and systems were built. So the first laser diodes that were actually used in undersea repeaters were built here. In the 90s, Nortel Networks owned the site, and there were 6,000 people just working on fiber optics and active devices, developing a lot of the development of hermetic packaging of diodes was done here. Then in the 2000s, we have in our area, we've got 26 Coherent, we've got SciFam Fiber Optics, Lumentum, Spire and Guggenhausgo, Prior Scientific, and Palomar. So there is a cluster of photonics companies, of which we are one, and we are located in a new building that was built and opened 3 years ago, which is called the Electronics and Photonics Innovation Center, in just across from the old site in Paignton of Nortel. And that building, that facility was built for incubating small companies such as ourselves. And it's not only a building which has laboratory space and units, office space that companies can rent, but also it actually has, and the intention was always for it to have workstations and machines, the latest type of workstations, machines for photonic packaging. So die bonders, it is one of the European centers for Palomar, the workstation manufacturer. So we have Palomar die bonders, we have Palomar wedge bonders, we have hermetic sealers, seam sealers, and projection welders. So we have access to absolutely state-of-the-art equipment, but we personally, as Bay Photonics, are often dealing with startup companies and R&D companies who need 1 or 2 devices from their 5 chips that they've had developed, but they are also needing to show a pathway to manufacturing in volume. So we can offer them, we can do semi-automatic, completely manual, and then we can develop processes on the workstations that they would find going to a large scale manufacturer. So why does quantum matter? I won't go into great depth into quantum, but it is a transformative technology across many sectors. Quantum computing is possibly the furthest into the future, but secure comms is here, and especially because of the worry of the future quantum computing, and the problem being that the concern is that if data is harvested today that cannot be decrypted, once quantum computers come along in the future, then they can decrypt the information. So the UK and indeed I'm sure many countries we have a committee of academics and security officials who meet every few months to determine how far into the future quantum computing is, so that they can assess the threat. But for now, there's a lot of activity going on in quantum communication or key communication. Sensing and timing and imaging are also other applications. And just to say that quantum is here and is out there in the field. Mount Etna has actually had a gravimeter, quantum gravimeter, monitoring its magma chambers for the last few years. This has been deployed and is continuously monitoring. So these applications are not all far into the future. A number of them are here today. And actually in the United Kingdom, the government were quite, let's say, at the forefront for a change in some of this technology. And we've been actually working on projects, collaborative projects for the last 8 years in quantum. So actually that means that we are at the stage now where some of the hardware, or the hardware that's being developed, is being productionized. And from PICs through to single devices like detectors and single photon sources, to larger arrays, and even we're very involved in getting larger, let's say, micro-optic type photonic sources packaged as well for cooling of atoms. So a lot of work is going on, and an overall thing when we're looking at the packaging and what has been touched on today about wafer level packaging and how to get to volume. Of course, with photonic packaging and quantum packaging, or photonic enabled quantum packaging, we have to think about the mechanical aspects, electronic aspects, thermal aspects, and the environment of the actual semiconductor as well, whether it's packaged in nitrogen in a vacuum, needs to be hermetic. And at the same time, we have to worry about the optical aspects, material characteristics, and those materials have to conform with all the above mechanical, electronic, thermal, etc. So the traditional packaging problems, and then with optics added in, and as I'll explain as well, then quantum optics added in. So I've done a small table here just to indicate some of maybe the semiconductor applications which are at the moment looking either at volume or getting to volume, and so compare them with quantum technology and the issues there. So if you think of a computer CPU, it's non-optical. Telecommunications, we're going towards what they call colorless technology, where all the components are wideband, so you don't need to have specific optical components for across the IT grid. LiDAR is eye-safe, so 1 or 2 wavelengths. Whereas from quantum technology, I have the challenge that I'm told it's very specific wavelengths, very narrow wavelengths, and as Martin mentioned, isolation. You cannot have any other photons other than those quantum photons. So these are challenges that are unique to quantum. In the environment, everyone is trying to go to non-hermetic. I mean, computer CPUs are, but in telco and LiDAR are non-hermetic. Again, a lot of these quantum new chips and PICs, if they're going to be deployed, they will need to be hermetic. And another thing is the temperature. I highlight the temperature. Most real industrial applications, -40 C is the minimum, whereas what we're seeing with the quantum is below that and down to millikelvin. So real challenges. And we're always trying to drive towards low cost, and I say to my quantum customers who will tell me, just we're going to leverage telecoms, we're going to leverage. You don't leverage that, you leverage volume. That's what you leverage. So, and I give them the example, if you build a new classical transmitter, you only get margin after 12 months in a production of 10,000 units per month. That's when you start to get low cost volume. So here are some quantum integrated circuits, or the media's view of quantum circuits. Of course, as anyone who works in photonics and PICs knows, they do not look like that. The chips are not suspended in midair. The photons don't fly through the top of the chip and just go somewhere. So there is a bit of an issue. We're in the marketing and what we're portraying as photonic or quantum chips, because in reality, these are what they look like in reality. One thing which is a big issue, and we know it's an issue, is that we know that in photonics and photonic integrated circuits, no one material will provide all functions. So it is absolutely critical to solve the chip-to-chip optical interface. And that will not be with fiber, because you are not going to, or not silica fiber anyway, you are not going to join chips which are right next to one another with optical fibers. I mean, this example on the right, top right, shows a perfect example of what you've got. You've got fibers coming in from the left. You've got the dark gray is the kind of photonic circuit, and the light gray array at the end is a detector circuit. So you've got 3 optical interfaces there. You've got, in this case, it's fiber butt coupled, but probably with a lensed fiber, and then the detectors are butt coupled. But that's the reality of these chips. That's what they're looking like at the moment. Low temperature operation in a vacuum, cryogenic. So we're talking about hermetic, and we're talking about looking at adhesives, solders at temperatures that little information is known. Input output count gets higher and higher. That is addressed in another way. And obviously at the same time, we need to get that light out of the package. So unfortunately, when I talk to my customers, I kind of give them kind of wake up call and say, well, when you're considering what you want, you have to consider the real world. I don't want to hear about hero transmission figures in the lab. You have to consider insertion loss, wavelength dependent loss, temperature dependent loss. What are your expectations there? There are various edge and surface coupling. The great thing about the chips is that you can pretty much have outputs anywhere, but please, don't put them anywhere. You need to really consider where your electronics and optics are going. So again, it would be helpful to talk to someone who packages before designing. Mode conversion is needed. Fiber arrays, I've seen people who want 200 strand fiber arrays. That this is not practical. There's a reason fiber arrays are made up of 12 fiber strands. It's because a splicer to splice them only goes up to 12. I think you can now go up to 16. But there are some limitations out there. And then AR coatings, standard packaging. When people say standard packaging, generally 1550, 1310 standard. You can get all the AR coatings, optics for that. Outside, that is not standard. And finally, is power versus stability. And this is something that was understood way back in the early days of diodes for fiber communications. yeah, you can get the highest optical power, but that will be a very unstable kind of trade-off there. So not the best thing to go for highest power when you want stability. So some of the actual work that we're doing, and this is addressing, so SPADs are single photon avalanche detectors, and they work at low, or for noise, to get the noise down, you need to work at low temperatures. So we're asked for -50 C operation in butterfly packages. Now, butterfly packages weren't really designed for that, and to get down to these low temperatures, we've had to use effectively evacuate the hermetic package to get down to the -50 C and develop techniques for that. But these, you know, these projects are ending up in real deployed systems. This was announced earlier on this year. BT and Toshiba, both companies that we work closely with, having the first commercial quantum key encryption connections between offices in, I think, London and Slough. Another SPAD project, and this time it's free space. So this is a project AirQKD where we're looking at free space in a building-to-building communication. Again, low temperature operation. So we have to put these devices vacuum in a vacuum, operate them in a vacuum. And in this case, they're in TO cans. And this is one of the interesting issues here, where we're putting the very, very leading edge, cutting edge semiconductors in packages that were effectively designed in the 1950s for photonic packaging. So there needs to be, you know, more work in that area. Spider project is where we're doing arrays, again, an array of SPADs with readout ICs. So as well as being low temperature, 400 connections, it needs to be transparent, and it needs to operate at minus 50 degrees. So these are all real quantum products, and they're let's say they're maybe the single discrete devices. So then you come to the PIC devices, and as I say, they can have inputs and outputs from fibers to detectors, and they can be designed in a let's say on the fly. So what we have to use are very, very manual at the moment for the prototypes, very manual precision workstations of our own to actually package these devices. And as I say, we're often asked just to do 5 devices. So it's not the easiest way to develop a process with 5 or so devices. So some of the problems in quantum that I'll touch on. I've been working in photonics for 30 years, and the cry has always been, please, more power, more photons. Not in quantum. In quantum, they want single photons. So when it comes to test, measurement, and assembly, how do you test the performance of a single photon emitter? None of the test equipment that's been designed, say, for telecoms or any other photonics is really designed for single photon. How do you measure the wavelength of single photon devices? How do you optimize transmission in an optical system, which could be a silicon photonic bench to larger micro-optic systems? When you're optimizing transmission with single photons, this is not a simple task. And then the optical component performance of real world components. Actually, when you start to interact with real components, low loss, and I'm saying low loss components in for example, in telecoms, your single photons will not last very long. And even optical fiber has loss. So that's why to date, the QKD demonstrations and communications are usually point to point, and they can't be amplified. And then there are other issues. Working in the classical world with our free space quantum key distribution, how do you filter out the sun? That is not a simple task to do. So these are problems that we're beginning to see, which really people could have thought of beforehand, but it's really only when you get the devices in your hands and start deploying them that you really hit the wall. So what are the technologies that are going to help us out? And this has been touched on in some of the earlier talks. The two photon polymerization, the nanofabrication, which a lot of it has come out from the Karlsruhe Institute of Technology, and there are a number of companies now, Vanguard, Multiphoton, Nanoscribe out there. And this is great because this is a solution to the interchip connectivity. And then the ability to develop, this is very recent work out of Karlsruhe, to be able to directly write onto the fibers, optical components, fibers and detectors, for example. And this shows light coming out of fibers and being run into VCSELs, and optics has been written onto the VCSEL array as well as onto the end of the fiber. And this is really groundbreaking technology that will be able to solve some of the issues there. And then, of course, those are 3D additive 3D. There's also other technologies that are more kind of wafer aligned to wafer level. This is Icon Photonics, who've got another polymer to do similar type of thing, but on a lithographic wafer level. And then another thing that's been mentioned, and this is what we want to be doing and are doing, is working with the manufacturers of the workstations. So actually make your platform designed for automation, for compatibility for day one. Have open carriers rather than boxes you're putting things in. Look at, rather than gold boxes, glass composite structures, where you've got a low cost for small volumes and a road to low cost for high volumes, and a reduced development time, because you can then actually develop your initial prototypes in a package that you can transfer to high volume manufacturing. And with sustainability, there's not much more sustainable as glass that uses sand. I won't dwell on this. It's just we're going to higher and higher input outputs, and there are technologies was mentioned right at the start of the session, 2D, 2.5D, 3D. This is all something, a lot of investment is needed to make this compatible with optics, and I'll certainly say that. But these technologies are out there, and this is the processor guys are really driving this. Touch on standardization. It's great to think about standardization. We probably aren't quite there with QPIC, well, certainly not with QPICs, but with PICs. It has been thought of. There was an EU project I was involved with back in 2010 called Paradigm, where we looked at PICs and how you would have a layout with optics, high speed DC inputs and outputs. We were too far advanced. In reality, people develop PICs, and at the moment it is the Wild West. And what I will always say is don't panic. We'll look at your one-off devices, and here's a great example. You've got Microsoft doing this type of device, and when I look at this and the bonds, that is certainly not following any standards that anyone would want to use, but it's pushing back the boundaries of quantum technology. So we're prepared to do that. So my takeaway here is quantum applications are here. There's a significant investment, and it's increasing in the EU, in China, in the US. The requirements for QPICs are somewhat divergent from other semiconductor technologies. Some of these state-of-the-art PICs we're packaging are going in packages designed 30 to 70 years ago. So we really need to move on. A lot of money has been put into developing chips, not much into developing packaging. But there are new emerging technologies that will address some of these issues, especially chip-to-chip and chip-to-fiber. And last thing I'd say there, that's where we are, the southwest coast of England, in the Bay. And as Patrick said at the start, it's difficult sometimes to find people who do packaging. You're welcome to come in and visit us. Bring your surfboard and your swimming gear. So that's where I will end.
All right, thank you very much, Andrew, for your nice presentation. Very interesting. We have some time to look at questions. There's one question in the chat from Guy van Straten, who asks, the temperatures mentioned are in the range of -40 to -50 degrees C. Is there also a high temperature consideration?
Oh no, that's very good, that question, because actually in the quantum applications that we've been asked to work on, I have never been asked for a high temperature application. I mean, high, it's all relative. I guess all these type of packaging traditional, let's say, more packaging techniques, up to, you would expect them to go up to around 100 C, but I've never. It's a very interesting question, because I've never had someone ask me to go to high temperatures. It's always, at the moment, in quantum anyway, to low temperatures.
Okay, Martin Schell raised his hand. Martin?
Yeah, thank you, Andrew. Thank you very much for the talk. From your point of view, which of the quantum applications do you think will be the first one to ramp up in production, so to really be installed in the field or used commercially? And second, what order of magnitude yearly volumes would you estimate for that? Do we talk about thousands, 100,000, millions of pieces?
Yeah, I think what I'm seeing, so some sensors, imaging sensors, LiDAR imaging sensors, but not high volume ones, not the ones going on autonomous vehicles. I'm seeing real applications, for example, in greenhouse gas monitoring, where the applications are going to be thousands per year. I don't see them as being hundreds of thousands per year. Even so I can, those applications are kind of here and coming and using, and because they're able to use the let's call them I'm sure the semiconductor people will hate me for saying this, but the simpler components, so discrete SPADs, single photon detectors are there. So that is going to be, I think, thousands per year, and is here. And then the communications, quantum key distribution, again, is here, but again, it just cannot be more than several tens of systems being deployed, because, as I say, this interaction with the real world, people have to be realistic. You can't just connect into the current classical, I call it classical telecommunications network, because you'll lose your photons. And there are ways of kind of getting around this by using satellites and distributing keys by satellites. But again, that's a very expensive thing to do, and you're not going to deploy a lot of satellites in a year. So I think, to me, the communication, some sensing applications, and it's going to be, at the moment, thousands per year.
Hello again. We are going back to the show. Hope you had a nice coffee break. Now the idea is to introduce the second part of the photonics session. We will have two speakers. So the first one is Bob Conner, who is VP New Application Business Development from the company Xceleprint. Bob will talk about microtransfer printing for compound semiconductor in 3D HI microsystems. Then we will have a last talk on photonics by Daniel Liske, who is senior expert in advanced packaging from Hemtech. And Daniel will speak about high accuracy placement for photonics and RF applications. So once again, when you have questions, you can ask during the presentation or after the presentation using the Q&A chat. Bob, the stage is yours. And thank you.
Great. Can you hear me?
Yes, we can. Thank you, Bob.
Okay, let me share my screen.
We can see it.
Okay. Okay, thank you very much for the opportunity. Microtransfer printing targets analog 3D HI microsystems. So we're really targeting the remaining technical barriers, which is the optical and RF communications, power delivery, and thermal technical barriers, not targeting digital. So, compute and memory is being well addressed with advanced CMOS nodes and advanced packaging. So analog, broadly defined to include photonics, discrete sensors, is a very large market that has much different technology requirements. Requires tight integration of large arrays of ultra-thin, diverse components, which we refer to as X chips for transfer components. So these are made on compound semiconductor, source wafers, SOI. They include passive components, include like microdiamond heat spreaders. They have much higher current density. So RF power transistors are pushing north of 10 amps per millimeter square, but lower I/O density. So it does not require ultrafine interconnects, but smaller form factors in the X, Y, and Z dimension. So the approach is to use the Z dimension for vertical heterogeneous integration of these large arrays of components. The X chips can be made on source wafers with the optimum materials or process technologies and nodes. And MTP is a massively parallel pick and place process. So it combines X chips from one or more source wafers with different process technologies, as illustrated here by the red and blue X chips. And the source wafers can be a CMOS IC, could also be a wide range of substrates, silicon, glass, ceramic wafers, and even large area glass panels. And the one or more arrays are integrated on top and then interconnected with a over the top, since the X chips are ultra thin and active side phase up. They can be readily interconnected over the top using the standard copper redistribution layer technology. And in fact, there could be RDL, multiple levels of RDL, and RDL could be on the source wafer prior to MTP trace placement. So you wind up with RDL on both the underside and the top side of the X chip arrays. So XFAB's published some nice papers talking about GaN on SOI 3D HI. MTP addresses one of the fundamental challenges, which is efficient integration of different size wafers. So this example is showing, say, a 200 millimeter GaN wafer that's tightly packed with X chips with very high wafer utilization. The stamp itself is, this example 40 by 40 millimeters, has a large array of posts, which matches the placement of the X chips on the SOI wafer, which is in this example 300 millimeter, with the SOI beamformers and a very high source wafer utilization, also high throughput, about almost 4 wafers per hour can be populated with this massive parallel pick and place with high placement accuracy. They're typically 1.5 micron, 3 sigma. So the throughput is greater than 200,000 X chips an hour with very high yield. Placement accuracy can be sub-micron with a trade-off in lower throughput. So MTP then could also enable multiple levels of 3D-HI, which really helps resolve the yield challenge with the 3D-HI microsystems. So as I mentioned, there could be multiple source wafers with different sizes, technologies, do the minimum amount of processing, minimum interconnects on the source wafer, and then make a first level 3D-HI component, which is a tested and prior to subsequent integration, so hence it's a known good die. So this 3D-HI then bridges the interconnect gap, which is due to wafer fab interconnect technology is ultra fine but thin, and going to say panel level interconnect that can have very thick copper interconnects, but they're coarse. So this intermediate first level then helps bridge that interconnect gap, and the second level can really be enable very low cost 3D-HI platform by going to a large area panel, and then also bring in glass and some of the superior properties of glass for particularly RF applications. So 3 examples. Patrick's talk was at 3 a.m. my time. I'm in North Carolina, so unfortunately I missed it. But Tyndall's done a fair amount of work with microtransfer printing for photonics. Another example is 3D-HI RF microsystems, and for 5G, 6G, to go to high frequency really requires tight integration to minimize the parasitics between the gain power amplifiers, SOI beamformers, and patch antennas. So the MTP is ideal for this heterogeneous integration of GaN and SOI, and populate, say, the bottom side of the glass with 3 glass vias with a large array of GaN on SOI-X chips, and then the top would be the large array of patch antennas. Another example, which is similar construction, would be power management. So power stage. So a half bridge, which is kind of a fundamental building block, requires tight integration of power transistors, gate drivers, and capacitors. So the approach is break up large components into a large array of small components, increase the source wafer utilization by moving the interconnects mostly off the semiconductor wafer area onto a large area glass substrate, populate the bottom side with a large array of, for example, GaN power transistors, the top portion with gate drivers and capacitors, and now you can reduce the interconnect between the thickness of the glass, which is going to less than 100 microns. So Accelerant's business model is to license technology, which in the portfolio includes over 650 patents. The technology was originally developed at University of Illinois, Urbana-Champaign. So for non-display applications, Accelerant provides a license, technical assistance, stamp production, prototyping service at Micros in Research Triangle Park, as well as Tyndall in Cork. And then X Display, our sister company, is commercializing micro LED components and also licensed technology for display applications. It provides microtransfer printing systems. So going through the manufacturing steps, so I'll briefly summarize each of these 6 steps. The first is to fabricate the destination substrate. So as I previously mentioned, these could be CMOS ICs, it could be interposers, wafers or panels. The X chips are placed active side face up. There can be diversity of X chips integrated on the substrate as shown here. The source wafers can be fabricated on X chips fabricated on a wide range of different source wafers, different technologies, materials. The source wafer has a release layer, which is chemically removed with a anchor tether system that temporarily holds the large array of X chips. So this would be, the anchor tether system can be fabricated using a couple of different process technologies, either dielectric tethers or photoresist tethers, as illustrated in these 2 diagrams. The release layer is etched away using standard MEMS technology. There's a wide variety of different release layers. They could be lattice matched to the source wafer, as shown in this table. And it varies with the type of 3.5 component, or with SOI components use the different crystal plane orientations. So the dry chemistry etches the release layer and singulates the device. So eliminates the need for conventional dicing. The microtransfer printing stamp is made out of elastomer material. It's a PDMS material. The stamp master is formed on silicon, so it's a very low cost process to cast the stamp master to form PDMS. It has a large array of posts on a glass substrate. So the post array size and pitch matches the desired X chip placement on the destination substrate. The stamp with the glass is stiff in the XY dimension, which really enables very high placement accuracy, but it's compliant in the Z dimension, which accommodates rough, non-conformal destination substrates. So there's two system suppliers that provide MTP systems. ASM and Migra has the Nova Plus platform that has MTP. This is a high throughput system. Supports up to 3 millimeter source wafers, up to 450 by 450 millimeter destination substrates. Got high placement accuracy, fast cycle time. ASM and Migra also offers a nano system for photonics that has finer placement accuracy. The second is X-Display. So X-Display, with a focus on micro LEDs, is offering MTP systems that go to even large area panels up to 1500 by 830, and the cycle times are reduced to say 10 to 20 seconds. XDC has a couple dozen MTP systems being installed worldwide. So MTP, the PDMS array of PDMS posts, principle of operation is adhere to the X chips with the temporary tethers and anchors on the source wafer via van der Waals forces, and the stamps viscoelastic behavior with fast separation speed picks up the array in the pickup regime, and the slow separation speed then places the array on the destination substrate. So this is akin to putting on and taking off a band-aid. So the stamp pickup breaks the tethers, removes all the X chips. The large stamp provides massively parallel pick and place. We handle very thin, very fragile arrays of X chips. The stamp, the destination substrate surface principle of operation could be for ultra smooth substrates, van der Waals forces are sufficient, or for rough surfaces, use an ultra thin adhesive. And then the placement can provide geometric magnification or fan out, which I'll explain in a moment. The MTP process can integrate X chips from multiple source wafers, so you can see the red and blue ones intermingled on the destination substrate. So the geometric magnification is shown here. So on the source wafer, the X chips are densely packed, and typically this only needs to be about 10 microns, or so spacing, just enough to let the etchants through to the release layer. And then on the destination substrate, with this X chip, 1 out of 16 array, the X chips then can be spread out. So the ultra thin X chips enable multiple levels of copper RDL over the top, and this is used done using a conventional seed followed by electroplating process. So MTP they can create devices that are or modules that are ready for bumping, so could fit seamlessly into the downstream packaging ecosystem, or be heterogeneously integrated in a system and package. So this video shows a the actual system. Let's click on it. Okay, and so then the process repeats itself. So this cartoon video shows the 3D-HI of different components. So these are two different source wafers, different process technologies with different size X chips. Right in below. So note the stamp is different in from the first source wafer to the second source wafer. So a different size array of posts, and then the copper interconnects over the top. So there's been multiple demonstrations and installations. About 10 years ago, the predecessor to Accelerant, Semprius, disaggregated a large triple junction solar cell into a large array of very small ones. Microtransfer printed on a ceramic wafer, which is the first level of 3D-HI. Then dispersed these array of triple junction gas cells on a large area glass panel for a concentrated photovoltaic system. And there was a number of field installations, passed all the reliability tests. If you're a high conversion efficiency, unfortunately, the solar market, the CPV market in particular, did not materialize. So that was the end of Semprius and the birth of Accelerant and X-Display. So Micros has MTP systems in RTP, North Carolina, and Micros has been doing 3D-HI for many years. XFAB in Erfurt has a microtransfer print pilot line for wafer level integration. Tyndall has a microtransfer printing system in Cork doing photonics heterogeneous integration. There's been numerous papers, technical papers published. This is a good paper talking about fan-out packaging using microtransfer printing. XFAB has published some papers on heterogeneous integration of GaN and silicon for both power management and for RF communications. And then Tyndall and others have done published a number of papers on use of MTP for indium phosphide heterogeneous integration on SOI. So the benefits are MTP increases performance. So this is by disaggregating and reintegrating large arrays of separately manufactured components, each one using the optimum technology, and then reducing the interconnect length that reduces the parasitics, that reduces the loss between diverse components, and then interconnect them with ultra thick copper to reduce the electrical and thermal resistance, and then this can fit into subsequent advanced packaging technologies. And this really enables advanced topologies that are just not possible with conventional packaging. So MTP decreases the cost because it really enables low-cost manufacturing processes, decreases the X-chip complexity, die size. This is really particularly important for emerging materials and compound semiconductors. Increases source wafer utilization. Geometric magnification really provides the benefits of fan out, but without the die shift and epoxy mold epoxy mold compound challenges. They can decouple the wafer fabrication with a 3D-HI, handle different wafer size mismatches in process temperature constraints. And then, as I mentioned, enable multiple levels of 3D-HI, make a very small known good die component, and then bridge the interconnect gap to really enable very large area panel level processes for subsequent 3D-HI. MTP accelerates time to market. You could have a library of source wafers with large arrays of X chips, and then by customizing the stamp, make a wide variety of different products. So large number of different RF arrays, large number of different power management SKUs to handle a number of different outputs, different currents, power, etc. And then really this process facilitates the lab to fab transition of innovative materials and devices. And then MTP also really facilitates innovation and workforce development. There's low-cost R&D systems that ASM and Micra and X-Display offer, and a number of universities, startups, research institutes, can readily bring this technology in-house for training and workforce development. So in summary, MTP enables employs low-cost, high-throughput manufacturing steps. The technology has been proven with multiple installations and demonstrations. It provides performance, cost, time to market benefits. Provides efficient 3D-HI of different size source wafers and geometric magnification.
All right, thank you, Bob. Thank you for this presentation. Very interesting. We also have one question in the chat from Jeroen Duis. So his question is, where do you envision an MTP system to be utilized in combination with heterogeneous integration with silicon photonics? Would that be a front-end silicon foundry, or would that fit in a back-end line assembly and packaging?
That's a great question, and I think it could be either. This 3D-HI is really opening up this middle end of line, which could merge with the front end of line or the conventional back end of line.
So it's yet undecided.
Well, I think it's really different customers have different philosophies and appetites. So I think we're agnostic and will support either the front end line or back end of line customers.
All right. Do you see any the tethering. So the X chips are not, they may deviate somewhat from the standard. So I guess the front-end foundry providing the X chips, they have to do some additional steps. Is that something that is easily addressed?
Yes, that's part of what Accelerprint provides. So we work with the wafer fabs in the optimum release technology, the optimum tether anchor design, and we've done that on many different material systems for many different applications. So that's really part of the technology transfer.
All right. I don't see any other questions in the chat. Maybe just a small question. What is the largest size of X chips that you can accommodate? So you showed an example of 0.6 by 0.6 millimeters. What would be the limit of that?
Not exactly sure the upper limit. There's been some work going up to about a millimeter. The approach, though, is because of the parasitics, break large chips into arrays of small ones, move the interconnects off the, as much of the interconnects as possible off the expensive semiconductor wafer area to the inexpensive destination substrate, so you could then get the benefit of much thicker copper, because many of these applications, it's imperative to minimize the electrical and thermal resistance in addition to the parasitics.
All right. Yeah, that's clear. Thank you. So if there are no other questions in the chat, I believe not, we should, in view of time, continue with the next speaker. So our next speaker is Daniel Lieske. He's a senior expert in advanced packaging at AIMTech, and he will discuss the high accuracy placement of parts in photonics and RF packaging. Daniel, please go ahead.
Thanks a lot. Can you hear me well?
Yes, excellent.
Okay, good. Thanks for the introduction and also for the nice talks before. Very interesting to see the evolution of photonics, of course. So I will now talk a little bit more of packaging itself, and photonics is part of it. I don't know. Do you see? I'm a little bit confused. Do you see all these screens, or do you see the full picture of the presentation?
We see the full presentation.
Okay, that's fine, because I have your nice heads also on the screen. Okay. Great. So let's talk about a little bit of packaging. Let's say.
No, maybe I'm sorry. I also see the heads, but I thought that were the heads in my screen. So now I'm not sure what I'm seeing.
No, actually, you are in full screen mode, Daniel.
Okay.
That's fine. Yeah.
So everything is fine. So I will start with a short introduction and give a little bit of an overview about AIMTech. And our next one is the high accuracy placement capabilities we have, and of course some examples of optical packaging, photonics packaging. Not so much about RF packaging today, but yeah, it's comparable. And a summary. Yeah, if you talk about optical packaging, a general message is that high accuracy placement is key for photonics packaging. Of course, I see a lot of ongoing works from Intel, IBM, and now GlobalFoundries is part of this photonics wafer pack processing. Of course, the presentation from Tyndall also showed a lot of nice work. So flip chip packaging and the packaging itself and high accuracy placement for packaging there's a rising demand. That does not mean that you only need the high accuracy placement. So you need to know how to handle the materials as well. Another general view is from my side. So of course, photonics IC packaging, the main problem is that the costs of the packaging is maybe above 80% of the whole system. So the packaging cost is the main driver. Of course, data center and so the development of data center and optical plugs is driving that a lot. As I said, for PIC placement, also the flip chip packaging is, of course, the demand of high accuracy flip chip packaging is increasing. It has advantages to use a PIC with solder balls instead of wire bonding, because the signal length is shorter and the interconnect density and pin count is increasing. So one day wire bonding will be not the right solution for PIC assembly, of course. But nevertheless, we see still, because of cost and yeah, bringing that into production, we see still that VCSEL processing and placing photodiodes very accurately and TS and lenses is a big business still in comparison to photonics packaging. Photonics packaging is still under development, and in the next years there might be some more products coming to the market. As photonics, but nevertheless, for both the photonics packaging or the PIC packaging and the VCSEL packages, the general issue is that the fiber attach, is one of the drivers for driving the costs. So it's single piece fiber by fiber placement, and it adds a lot, of course, to the package. And to get rid of it, it might be the solution were shown already, that optical fibers are placed into V grooves, but still the fibers have to be placed to the PIC very, very narrow, so within 1 micron. So still there's very high accuracy needed, but it can be, and that's the message here, it can be passively aligned to the PIC. Of course, here are some nice pictures from IBM. The general, how the package should look like is, in general, I imagine a BGA package fully capable of doing reflow of that package afterwards, but that's still another challenge. So the fibers need to be reflow capable as well, if they are already assembled to the PIC. So the EGA package itself can be a glass, silicon, or organic interposer. This example from IBM shows an organic one, but we are working also on glass interposers. So what's high accuracy placement? What does high accuracy placement mean? Just to give some ideas. So we are working on high precision flip chip packages or die attach packages. I mean, die attach is mostly the VCSEL placement, and photodiodes, as mentioned, they have to be very tight in X and Y. Not so much in theta, but for this components, X and Y is most interesting. For fiber attach, also the Z component comes into place, because any micron difference in height makes a real difference in signal performance. High precision means also, the cost is going up because the throughput is going down. So it's always a compromise how accurate it must be, and yeah, to keep the cost down. And last but not least, we need to know the interconnect, how the interconnects have been done. Is it soldering with solder bolts or with copper pillars? We have gold stud bumping with thermocompression bonding in place here for high precision bonding. But anyway, to keep the cost low, it should be done with passive alignment. Little bit about MTech. So we have production floor space of about 3,000 square meters, and most of the high accuracy placement is done in ISO 5. We are 220 employees, and yeah, let's say working since years, and have more than 60 customers with more than 500 realized products. So we are really focusing on packaging, customized products, don't have own products. So these are all custom specific ones. Our portfolio, which is needed for packaging and also for photonics packaging, is we have a part which is called wafer backend that deals with wafers. We are doing underbump metallization on any kind of wafers. Put the solder bolts on them. Can also, before underbump metallization, can offer the redistribution layer, which are needed for standard wafers. And in a partnership with Fraunhofer, we can also offer the fan-out wafer level packaging. Gold stud bumping and wafer dicing is part of the wafer backend as well. So, and then when it comes to high precision packaging, there are these two solutions, the flip chip and the chip on board. Flip chip, of course, with solder or gluing. So there's still there are other methods of flip chip mounting, so can be done with an silver conductive glue, ICA, or maybe with an NCF foil, which I will show later. And the chip on board and also the high accuracy chip on board is done finally with wire bonding. Everything ends up with the whole packaging. So we do BGA packages where we need the BGA balling, and we have these additional SMT placement in combination with the high accuracy placement packaging. And there are large modules we produce which deal with very complex systems and sensor elements we have to place also with high accuracy. Everybody knows these nice pictures. The placement accuracy which you can reach is much better than the dimension of a human hair. So here's the comparison of 1 micron spot to a hair diameter. Our equipments are capable of going down to 0.5 micron placement accuracy. And in fact, we have large floor space in the production. Actually, it's still growing, and we are having 8 equipments with different placement accuracy. So, but all are below 3.5 micron placement accuracy. So it's really focused. We are really focusing on production. And all our customers who need high accuracy placement, they may know, and I always ask or teach them again, the accuracy is not only the equipment but it is beneficial to have a low temperature placement process like the ICA gluing instead of soldering. And it's also a matter of force, of bond force, that makes the higher bond forces can make the placement accuracy worse. Still, we have some issues sometimes with substrates and fiducial qualities of substrates. So that is very important to talk in advance to customers and talk about the right fiducials for, let's say, 0.5 micron placement accuracy. Stable environmental conditions is mandatory, of course, and depending on the application, the choice needs to be done in advance also, if it needs to be an organic substrate or it needs to be a glass or ceramic one. Silicon, of course, is very ideal in terms of low CTE. High accuracy also means after placement, you need to UV cure materials, and that have to be thermal stable after curing and withstand further reflow processes. So we know how to do that as well. In my opinion, if you are talking about interconnect technologies, there are indeed several of different. What we mainly see is that the adhesive bonding technology of VCSEL, photodiodes, TIAs is still the best and can be in a pretty high accuracy range. There are examples where thermocompression is also feasible, but in general, to keep the cycle time low and the cost down, the soldering is even better for high accuracy flip chip placement. But nevertheless, if it is required to have this, if you don't are allowed to have those self-alignment during soldering, you can do that, of course, by soldering it on a tool, and then it's in a cycle time of a thermocompression process. So then both are very equal. The benefit of soldering is still that the force is quite low and the chip will not move on the substrate during bonding. So, but we are dealing with adhesive bonding, thermocompression, soldering mostly. The other processes, pressure silver sintering, and hybrid bonding is still under development. Now some examples where which processes we use for which kind of target placement accuracy. So there might be products where still 25 micron placement accuracy is enough. So here we place chips, photodiodes onto wafer, so a chip to wafer process, and do a mass reflow. The self-alignment doesn't make it worse than 25 micron placement after reflow. There might be X-ray detectors we are dealing with where it is enough to have 20 micron placement accuracy. This one is again an adhesive printing and cold start bumping process. Can be done at very low temperatures, at about 100 degrees C curing temperature. After that, it is reflow capable. So a very good solution also for optics, in my opinion, in the future for PICs. For telecommunication, those optical cables we produce are with TIAs, VCSELs, photodiodes, optical lenses. They can be passively placed with an accuracy lower than 7 micron. It's an adhesive process. The lens is working as an micro-optical interconnect as well, and is having V grooves, and these V grooves, so the fibers afterwards will be placed into V grooves, completely passive. So that is for different kinds of products doable. Some optical repeaters we could manage with an accuracy of below 3 micron. And here we qualify the gold stud bumping process we have in-house and the thermocompression bonding. There are some specialities. These are still optical applications, but yeah, not photonics in that way. But those VCSELs or VCSEL arrays, there are requirements of having them with an accuracy of ±5 micron, and this has been done with reflow soldering, completely fluxless. I will show a picture of that a little bit later. So it's feasible to do that with solder also. And since years we provide VCSEL light sources for semiconductor industry, and there's an adhesive ICA stamping and placing the chip. Yeah, the best choice. Now some examples. Those photodiodes are used for CT scanners, X-ray CT scanners, and they are done with they are provided with gold stud bumps. These gold stud bumps are bumped with KNS stud bumping machines. So we having 2 of those high volume capable machines for doing those nice gold stud bumps. Large photodiodes, so this is in a range of 22 times 15 millimeter die size is also doable with that process. Coming a little bit more to the photonics. This is a glass substrate where we place the tiers and VCSEL arrays bottom down to the substrate. Those glass substrates are gold stud bumped before, and the tier is placed like a flip chip, and the light is going through the glass to the opposite side, and on the opposite side the fiber is attached. Also with thermocompression, as I mentioned, the temperature is very high, the pressure is very high. It can be done with an accuracy of ±2.5 micron, which is shown here in this diagrams. Just to give you an idea, so the stud bumping thermocompression bonding process looks in a cross section like this. So this is on a flex substrate. This has been done on a flex substrate. It looks like it's a little bit wavy, but that's, yeah, when you do it on the soft substrate. The shear force of those chips is very good, and the shear mode shows that the stud bumps are well bonded to the substrate, and here more or less the chip was sheared off, and the stud bump remains on the substrate. An electro-optical cable. And here the demonstration. The product itself. We could demonstrate that the passive placement of all the components, as well as the MOI, can be done, and the fiber array attachment into V grooves is good enough to have a nice electro-optical cable. Other examples for data sensors are those pluggable devices. They are equipped with VCSEL or VCSEL and tiers as well. So some different kinds. We are dealing in the wafer backend. We are dealing with photonics wafers as well. So this has been done in a project funded from the BMBF also. Here our part is to do the underbump metallization on wafers. Here's the edge where the fibers will be coupled later. We are doing the solder ball attach as well and the flip chip packaging. And finally, it's kind of BGA package seen here. Another benefit is for the solder ball attach that we are free of doing. So that's a microsphere solder ball attach. We are free to use any alloy which is available on the market. If there are chips which are not feasible to withstand temperatures of above 200 degrees C, here the possibility is to use low melting solder alloys instead of SAC305. Still, this is not photonics, but still we are dealing with photodiodes. So those products are under volume production here at MTech. Very complex things with final encapsulation. This is an implantable device for blood sugar measurement. You see how small it is, and that are some. Then you have some more ideas about what we are doing. The VCSEL placement on ceramic substrates can be demonstrated here. It's a fully void flux-free process where we solder the VCSEL diodes to a substrate and place them with a very high accuracy. And during reflow, we could develop the process. The VCSELs are not moving anymore, so we can reach placement accuracy after reflow below 5 micron. Another specialty of this is the wire bonding of those VCSELs with a very flat loop, and of sometimes it's getting 3-dimensional. So this is a wire bonding onto the edge of the substrate. So you need to place the substrate vertically and wire bond it. Maybe not the first choice for photonics, but still it's possible to do ACF bonding of chips and also flip chips with photonics. Here is just an impression. The substrate is 430 times 350 millimeter, so very large, and the ACF bonding itself works that you have conductive particles in the foil, which you compress and squeeze a little bit, and the electrical contact is in between the substrate, the chip, which you see the pad of the chip here, and the conductive particles. What comes next? So no challenge is challenging enough, or we don't accept, or we accept all challenges, let's say. Like this one, this is a complex 3D package with optics and VCSEL placement, and finally an active alignment of metal cap afterwards. And this can be seen here. And so don't be afraid and challenge us with those products as well. The summary, yeah, optical packaging is also available in Europe. I'm very confident that there are much more companies working on that. CITC, of course, is an example. I mean, customers need to be convinced, of course, but they shouldn't be afraid. Or what we want to do is we want to do packaging in Europe. Investments are ongoing, and we just need customers come to us and give us new product ideas, and we can develop the right product with the right interconnect technology. In my opinion, the strong network in Europe is much of the importance. That's why I like this conference today. Let us work strong together in a strong network, and also we are part of these EPIC consortia, and I think they are doing a really great job. Thanks a lot.
Right. Thank you a lot. It was a very nice presentation with a lot of very nice examples to show what you can do. It would be nice to give people opportunity to answer questions in the chat. At the moment, there are no questions yet. Maybe if I can ask one brief question. So you showed in the beginning that you can do assembly down to the 0.5 microns. I think the example with the highest accuracy you showed was 1.5. Is the 0.5 really also needed in actual projects that you use now? Is that the fundamental limit, or can you even go lower, or would you need active alignment for that?
I'm not sure if if active alignment can be done with that accuracy, but the machine capability is 0.5 micron, so it's a fine tech machine. The actual requirements, so the example I showed was 1.5 micron. There we already placed over 4 million pixels with that accuracy, and that's the actual demand. So there was one optical packaging which was in the range of 1 micron, but not with that high volume. So it's challenging, but the machine capability is there.
And does it help for customers to engage with you in a very early stage to make sure that, let's say, the chip design or whatever materials used are not a bottleneck in achieving that accuracy?
Yeah, definitely. So for VCSELs, that is maybe you're gonna make so much wrong. But if you have a large chip and you want to place a large chip with a very high accuracy, so the fiducial have to be right, and they have to be on the right position. Also, if you understand how the machines work and how they do the alignment, you know how to have how to make the fiducials, and that we want and we need to tell our customers in advance.
That afternoon will be dedicated to RF packaging and power packaging sessions. So we'll start with the RF packaging one, and for this one I'm co-hosting with Francesca Giapni from CITC. So hello, Francesca.
Hello, Emily, and thank you.
So we will have two speakers this afternoon, and I will let Francesca introduce them.
Yes. So this afternoon we will have two speakers and three speakers for two presentations, sorry. The first presentation will be given by Ad Reiners and Sander Bronkers from the Eindhoven Technology University and from the company Antennex. And the second presentation of today will be given by Gabriela Pereira from Yole. So we can start with the first presentation from Ad and Sander. The title is Making Millimeter Wave and Sub-Terahertz Over-the-Air Characterization a Reality. The two speakers work both in Eindhoven, the Technical University, and from the company Antennex. Sander and Ad, the floor is yours.
Thank you very much. Can you all hear and see me and hopefully also see my slides?
Yes, we can.
Okay, perfect. Thanks. Yeah, so thanks, Francesca, very much for the nice introduction and invitation here. So as you mentioned, Ad and I are today here representing both TUE and Antennax, since a lot of the concepts that we develop at TUE eventually end up in the company Antennax. So today we will talk about well, our favorite topic, antenna metrology. So when I say antenna, I mean actually antenna in the bigger concept. So that could also be a bigger system, but with an antenna interface. And in particular, today we will be focusing on the higher frequencies, so millimeter wave, sub-terahertz, where it also intersects quite well with RF packaging techniques. So what will Ad and I be talking about? Because Ad will take over somewhere halfway during the presentation. So I will start with a bit of an introduction on why metrology is important for antenna applications. So why do we want to do this, and why is it important to do this well? And then I will shortly stop at a quick reflection on how design and measurement relate to each other, in particular from an antenna point of view, where we try to intersect simulations and measurements. But most of the talk will focus actually on 3 different measurement approaches. So one of them is how can you characterize the electric properties of, for instance, packaging materials at these kinds of frequencies. And then I make a distinction between measuring isotropic properties or directional properties. So the dielectric properties will be talked about by my colleague Ad, as will the directional properties. So why do we want to do antenna metrology, and why is it important to particularly focus also at the higher frequencies? Well, I found this image in the, well, at that time, so that was June, maybe by now they have a newer one, in the Ericsson Mobility Report. So as you can see, we've probably all seen pictures like these, right? So the amount of data that we use, uplink plus downlink, keeps on growing. And this is not a projection, this is actual data. So the year-on-year growth goes down a tiny bit, but still we need to keep developing new concepts in order to be able to supply this kind of demand. So what do? We go to higher frequencies as there's a lot of spectrum available there. And that also means we need new antenna solutions or new antenna system solutions. And that also means that we can make these solutions smaller. So we can start integrating them into a package, for instance, or really tightly integrated with amplifiers. So that is, of course, an advantage in that it makes the application nicer. We can probably make things a bit more affordable as well. But we will see it also has some challenges, of course. So let's take a bit of a look at what this kind of change means for an antenna measurement. So in the old situation, so here I'm talking sub 6 gigahertz, 4G kind of applications. We would have an amplifier, we would have an antenna, and for the application, we connect those two together. Now, the nice thing of having these two separately is that we can disconnect them and then measure separately our amplifier and our antenna. And why is that nice? Because we can measure this amplifier now in a conducted way. So all these nonlinear properties that we want to know about of an amplifier, we can do that in an extremely well controlled and confined environment. Now, if we look at 5G millimeter wave or even 6G systems, then we see that not only do we get more antennas because we now tend to work with arrays, but also that there is no separable interface anymore between the amplifier and the antenna. They become part of one tightly integrated solution. So now we have to measure everything in a radiated way. And we cannot even take these two apart, but we also have to deal with the fact that there will be multiple antennas on one usually rather tiny system. So that leads me to talk a tiny bit about the design process. So this is something that my colleague Ad proposed in his PhD thesis. He will talk more about it later. But basically the idea is that you start with some kind of configuration. So that could be for research purposes, or you want to have some system, or you want to fulfill some application, and it results in some requirements. And these requirements we can see as true values, because this is something that we stated, okay, this is what it has to be. Taking those, we can make a design. So we often do that in 3D simulation software tools that also allow us to simulate this structure from an electromagnetic point of view. And of course, we can then also fabricate such a device. Now, once we have fabricated it, we can, of course, also take a measurement of it, for instance, using an anechoic chamber, and we can compare our simulation with a measurement. So I would like to stress here that it is our belief that there is no completely correct, that neither the measurement nor the simulation is usually completely correct. So in the measurement, we will have uncertainties that contribute to deviations from the actual truth, but also in the simulation, we will have assumptions that have been made in the solver in order to make it compute in a kind of reasonable time that will also impact our results. So we can try to bring these two closer to understand better what is going on and to get more confidence in the results, but they will never be completely matching, and we can also never really state which of one is an absolute truth. Okay, so now I will look at the first, no, actually, let's go to our overview first, right? So if you look at our antenna system or at part of an antenna system, then of course we can take different approaches on how to characterize that. And it's important to realize that there is no one size fits all kind of solution. So we should really carefully look at which problem are we looking at. So what property do we want to know in order to find a solution? So we've identified key challenges over there and basically ended up with three main ones for these kinds of frequency ranges. So the first one is to know something about the electric material properties. So this is really, for instance, a packaging material would have this property. It does not depend on geometry. And then we have efficiency or power measurements. So this is really something about the system or about the antenna, about a particular design or the implementation of it that we want to know. And finally, we can say, okay, if we have this system, we usually also want to know something about the difference between different angles. So we want to characterize our device at different angles, maybe using different scan directions for our phased array, if we had one, to see how the system is behaving. So we came up with, in our opinion, the kind of ideal solutions for each of these challenges. So the electric material properties, we have a Fabry-Perot system for that, that Ad developed. He will talk about that later. For the efficiency or power measurement system, we have a downsized reverberation chamber for these frequencies. And for the measurement of directional properties, we have our anechoic chamber. So now I will first look a bit at this reverberation chamber, and then Ad will cover the other two. So why do we want a reverberation chamber? So I put a picture here of our smaller one. In the next slide, I will explain you a bit about how it works. But basically, this is a very nice way to measure what we like to call the isotropic parameters of an antenna or a system. And so these are parameters that are usually very hard to measure accurately in an anechoic chamber because you are trying to fight physics and have to integrate over a sphere. And the reverberation chamber kind of does that naturally for you, making use of some clever physics. So as we say, the reverberation chamber creates an on average uniform environment. Now, of course, we can apply this for EMC applications, which is where the concept of a reverberation chamber comes from. But we also can apply it, and this has been a up-and-coming topic in recent years, to antennas or antenna system testing. So think of antenna on chip, in package, or part of a system, complete arrays. And we can actually do that up to at least 140 gigahertz and probably beyond. So how does that work? So here we have the same picture again that I showed you just before with a zoom out. So basically when we want to do a measurement here, we close the room using a door so that we have a good electrical connection all around. And basically what we get is a resonant cavity. So we will get a field distribution inside this chamber with very high peaks and very low lows. Now, if we change the rotational angle of one of these pedals, so we have one here and we have one over here, basically the field distribution inside this entire chamber will change. So I took an example at a bit lower frequency, but it looks the same at higher frequencies. So if we have one single VNA sweep, then it could look like this. So this seems very noisy, but what we are looking at here is actually the high highs and the low lows that the chamber imposes on top of the antenna response. So if we then apply this, as we call it, stirring of the pedals to change the field distributions and do our averaging to get at this on average uniform field distribution, we get something that looks like this. So we did a comparison with the anechoic chamber measurement, and you actually see that, for instance, the S11 nicely converges towards the anechoic chamber response. So for S11, of course, you could easily measure that in the anechoic chamber, but the main advantage here is that this also holds for S21, for instance. So you will also get this integration naturally over all angles, over all polarizations, which is extremely nice when we don't want to know about a particular angle of an antenna or a system, but we're very much interested to know how much overall is being radiated by the system, or how sensitive is it to incoming signals. So we've, of course, adapted this to millimeter wave. So we've made our own design, really focused on minimizing the losses, because this adds up very quickly at millimeter wave. Currently, we tested up to 140 gigahertz, but the performance is still so excellent at those frequencies that we can probably go higher with a very nice field uniformity. So if you're interested in the details, then just let me know. I can always send you some more information. And what we also have included is a facility to probe antennas or antenna systems. So we can actually put a probe station into this chamber so that we can measure antennas or antenna on chip or antenna in package that do not have a connector in a reverb. So then we could have, for instance, just the antenna or an antenna with amplifier using a probe, but we've also done bits in, waves out systems, for instance. Now, of course, this kind of chamber is also not ideal, right? It might be a very nice solution for the problem we are looking at, but of course we have uncertainties that contribute towards our end result. So you can think of, for instance, components due to the instrumentation that you will also always have, like drift or calibration artifacts. But we also get some field uniformity that is not ideal yet. We can improve on that by playing with more measurement time. So there's a trade-off to be made there of the uncertainty that you're willing to accept versus the measurement time that you will get. Now, I think I will hand it over here to Ad.
Yes, thank you, Sander. I will continue from here. You can hear me?
Yes.
Okay, perfect. Well, I will continue with the verification step because the idea there is that we want to feed the model, the simulation model, with information from reality. So that could be production tolerances, but in this case, we zoom in on material characteristics, especially dielectric materials. If you look at those libraries that are available in these software packages, you see that they are normally characterized up to 10 gigahertz. And if you want to zoom into 5G, 6G applications, then we're already going up to 100 gigahertz. So we really want to know how the materials behave at those frequencies, what the loss tangent is, and what the dielectric constant is, or the relative permittivity. So you can go to the next slide, Sander. So this is an example of why do we material characterization. So how important is it to know exactly the material characteristics? And I think one of the things maybe that makes most or is most impressive is if you look at the loss tangent, that even a small deviation in the loss tangent can give you a significant different outcome. Almost, let's see, 10–15% difference in radiation efficiency. So if you want to estimate how your antenna will behave in the whole system and how efficient at the end the system will be, then this information is very important to have, and to have it accurately for the frequency that you want. And as we know that it will increase with increasing frequency, you really want to know how high the losses will become and if materials are still usable for your specific application. You can go to the next slide. Yeah. So the reason why we designed this Fabry Perot is what you see here is in the middle in the white, that's the holder for the material. And on the top and on the bottom, you see two mirrors. The idea is that via the waveguides, the golden colored tubes, electromagnetic waves are actually injected into the cavity. And there you get a kind of Gaussian beam with a certain beam waist or radius in the middle of the chamber. And in this case, it's 20 millimeters. And the idea is then at that area where you illuminate the material that you characterize the dielectric constant and the loss tangent. That's the advantage of this system, that it's a resonance system, so you can obtain both material characteristics that are important for instance, antenna design. Another advantage of the system is that you do not have to change or alter your material. So most of the materials you can put directly in here, and afterwards you can reuse it. And with many techniques for determining material characteristics, you have to change or put something on the material, and afterwards it's not usable anymore. But it does not mean that if you determined the material characteristics, that it also is accurate for a batch of material that comes from a production. So we think that, especially at millimeter wave, characterizing many samples is very important to also understand the deviation. Next slide. Another thing is that what we zoom in is that, of course, materials are not always, especially what we use for RF applications, are not always homogeneous or isotropic or have a linearity, are linear. So this is something to investigate, like what is the effect from those properties. Another part is that the effect, which was done by, the link is below, what is the effect of temperature changes? If you cycle it, about aging, so if the material becomes a year old or 2 years or whatever, what is the effect on the relative permittivity? And you see that there could be a significant change. In this case, the red one for the 150 degrees temperature, that could really give significant differences. So this information is also important. It's not that we are at the stage that we can do this, but it's something that we're aiming at to be able to perform controlled environmental conditions to be able to characterize the materials. Yeah, next slide. So yeah, that was the verification step. Then we have something Sander already mentioned, it's the validation step. So you want to compare the results from the measurement system with the simulation model. But of course, the measurement system will also have some uncertainties. So what we aimed at is to design a system that we can investigate that. Next slide. Why? Well, as mentioned before, millimeter wave introduces new technology, new possibilities, integrating antennas, integrating it in package, in system, creating arrays. on different materials covered by radome or package type. So you want to know what the effect is, or you want to characterize these antennas maybe standalone or maybe as a device. So how could we do that? Next slide. So we designed our own system. You see a spherical system. In the middle, in the blue, you see the electromagnetic absorbers. In the middle of the chamber, you see the antenna under test. And you see actually a way to perform a kind of scan around the antenna under test. So with the reference antenna. And the idea was, this is a complex mechanical design, and the idea was to let the chamber move around the antenna under test. And the reason we did this, because some of the antennas are probed, and it's very difficult to move a probed antenna under test around a reference antenna. So we inverse that, or reverse that, so that we have the chamber moving around the antenna. Another thing is that we try to place every supporting structure or motor outside the chamber, so that within the chamber it's as quiet as possible, no reflective objects, and as minimum as possible for the supporting structures. Yeah, you can go to the next slide. So here you see it in red, is an example of the probe with the antenna under test. So the probe station is underneath the chamber. So we have this complex structure to be able to move the probe, place it on top of the antenna so that we can measure it. I can say that this is always a challenge to get rid of the behavior of the probe on the behavior of the antenna. So even if you cover it with absorbers, somehow it will be affected. One of the things that we did is we incorporated the probe into the simulation model. And in this case, we were able to see the comparison again between antenna and the simulation model and the measured model. And that's what we call, do you want to characterize a measurement model or just a scientific model? Because otherwise you have to subtract the behavior of the connector or the probe. In yellow is the translation table. The translation table we use to be able to perform a planar near field scan. In the green top is, you see actually the yellow colored or gold colored cylinder. That's what we call the scan head, and that you place the waveguide holder, which is below. That's specifically designed for us. And in the waveguide holder, you have a batch of waveguides for certain frequency bands. So you change every time the waveguide holder when you want to perform in a different frequency band your measurement. This waveguide holder can rotate around its axis to perform, for instance, for circularly polarized antennas or for polarization, and it can move in the Z direction. And we use that one for determining more accurately the gain of the antenna. Yeah, you can go to the next slide. Well, we had it about uncertainties. So there are a lot of mechanical uncertainties. The chamber is approximately 2 meters by 2 meters and 1 meter in width. So there are some mechanical challenges to overcome. That was not always possible. So what we did is we incorporated cameras. And with the cameras, we can perform preliminary measurements to be able to obtain, to see the inaccuracy of the movement of the reference antenna. When we perform far field measurements, if we perform near field measurement, we can actually follow the AUT. And in this case, we can trace the actual position of the reference antenna or antenna under test during the measurement or before measurement, and we can compensate for that. So this is a research that we're still doing, and it's still ongoing. And the idea is to use it for spherical near field scan, which is also possible with this system. Yeah, next slide. Yeah, so we need tools that are can help us to validate what we try to predict with our models. And we think that the devices that we designed and investigated via the TOE and which we implemented via Antennics, that those measurement tools will help us to conquer the challenges in characterizing millimeter wave antennas. Well, you saw already the Sander mentioned key challenges and the solutions, and we believe in this way of characterizing millimeter wave antennas. Thank you very much.
Thank you, Atte. Thank you, Sander, for this very nice presentation. I would like to remind to the audience that it's possible to ask questions to the speakers via the Q&A box in the chat box. So if there is any question, then you can set it there, and we will read it to the speakers. Meanwhile, while we wait for the audience, I have a couple of questions myself on your presentation. You mentioned for your reverberation chamber that it's possible to measure on to 140 gigahertz. I was wondering, what are the frequency range for the other two setups that you discussed in your presentation?
Yeah, what we do now is the anechoic chamber we also characterized up till 140 gigahertz. For the material characterization, we're still busy with that, especially because, as Sander mentioned, for the reverberation chamber, the losses become significant in the material that you use. And yeah, the Fabry-Perot, the mirrors. So the question is, how much are the losses in the mirror? So at the moment, we try to characterize that to see how it affects the Q factor of the obtained signal. So that's still ongoing. So up till now, we were able to measure to 90 gigahertz.
Yes, thank you. I don't see any question in the chat. I have another one, and it's about the accuracy of the material characterization. If you can tell something on how what's the error bar on those measurements that you can get out of this Fabry-Perot resonator.
Yeah, what we did now, just to explain, so we try to find the uncertainties in the system itself, and of course in the material. And what I remember is that depending on the loss tangent of the material, and depending on the height of the relative permittivity, that we can obtain results better than 0.01 for the relative permittivity, and 0.001 for the loss tangent. So the lower the loss tangent becomes, the more difficult it becomes to determine it more accurately. And that also accounts for if it becomes higher, but yeah, there's something in between. So this is the accuracy that we can obtain at this moment.
Yes, thanks. I'm looking if there are any questions in the chat.
No. Maybe one from my side, maybe that's a stupid question. Do you see any chance to miniaturize the system that you developed on long term to make it more scalable?
Which system do you mean?
Oh, all the chamber and all the Fabry-Perot resonator.
Yeah, that's true. So if you go to higher frequencies, then you can ask yourself if you can make it smaller. But the problem is that you have to handle certain the material doesn't always become smaller if you have these plates. So you're limited a little bit by that. Concerning the anechoic chamber, yeah, that can become smaller if you go to even higher frequencies. That's true. Yeah.
Okay, thank you.
And to wrap up about the reverberation chamber, I am thinking of a smaller version, but of course there we also have a practical limitation in that you still need to be able to work in it. So at some point from the operating frequency point of view, yes, you could make it smaller and might even want to make it smaller, but it doesn't always have to be practical to do that.
Okay, maybe add one more question from my side. Marco Koeling speaking. You showed a slide in which you raised the issue of the effect of aging material, the aging of the material on the dielectric parameters.
Yeah.
Very relevant topic, I think. But the question is, when the material ages, obviously the parameters change, but does it also pose challenges on the measurement? I mean, is the material shrinking or changing that it also changes the accuracy of the measurement?
Yeah, that's a good one. So then you get a kind of paradox, like is your system affecting the measurement or other way around? So this is something that what you do is you create a kind of reference material to see that your system is still working as expected. And then you actually can use the material that's affected by. So you can affect the material on purpose, right? So put it into a climate controlled environment, and then, for instance, expose it to humidity or to UV or to temperatures, and then place it again in your measurement system. The question will be if, for instance, if the temperature is high, if that would affect your measurement system, because somehow your measurement system will be heated up. Yeah, those are challenges. One of the things that we can do, or what we did in the past, is we monitor also the temperature inside the cavity itself, and also the humidity. And we took that into account per measurement. So we cannot then completely explain it, but we have all the data in the circumstances that it's actually measured.
Yeah. Okay, thanks.
You're welcome.
Yes, thank you. And if I do not see any further question in the chat, so maybe we can move to the next presentation, given the time. Thank you again, Ade and Sander.
Thank you very much.
Yes, and the next speaker for this presentation is Gabriela Pereira from Yole Group. Her presentation has its title, RF System in Packaging Market Trends. Gabriela, please go ahead with your presentation.
Yes, hello everyone. So I will share my screen. Let me know when you can see.
I can see it.
Okay, very nice. So I'm Gabriela Pereira, and I'll be doing this presentation about RF system in packaging, market trends and technology trends. So first of all, let me show you what are the topics that I'll be covering. First, I will shortly introduce myself. I will make an introduction to the topic. So this will include RF system in package definition, RF packaging in mobile, and the main interconnections that are used in RF system in package. Then I will highlight the main market drivers, technology roadmap, and technology trends related to RF system in package for mobile applications. I will show you some system in package market forecasts, which are extracted from our market monitor, Advanced Packaging Market Monitor Q3 2022 edition. Finally, I'll do a supply chain overview and I'll show you the conclusions. So first of all, I'm a technology and market analyst at Yole Intelligence. I work in advanced packaging team, meaning I produce reports, and I'm engaged in some custom projects related to this topic. And previously, I worked at Amcor Technology in R&D department. So first, let's start with the definition of a system in package. I know that in the industry, this term can be a little bit confusing, and maybe some companies have different definitions. So at Yole, we try to reach a common consensus, and we call a system in package a combination of integrated circuits of different functionality, which may include passive components, active components, or MEMS, assembled into a single package that performs as a system or a subsystem. So system in packages can utilize a combination of different advanced packaging technologies, which include flip chip, wire bonding, fan-out, in wafer or panel level, embedded die, and at different configurations like 2D, 2.5D, or 3D, and even a combination of these configurations. So here are the typical system in packaging technologies. So we can have flip chip and wire bonding system in package, fan-out system in package, and even embedded die system in package. So depending on performance, costs, and time to market, one option may win as superior for SIP. We can see here that each one of the types of packages has different capabilities in terms of line and space, for example, because it's using different processes. So the one that can reach a more aggressive island space at this moment is fan-out. But this also includes a higher cost for production. So actually the most commonly used type of system in package, and specifically for RF applications, is the RF and wire bonding system in package. They are like the front runner solution and the most popular choice for cellular, even automotive, networking, and computing system integrations. So this will be the focus of this presentation, as it's the most relevant packaging platform. And you'll see that our forecast and all the technology inputs that I'll give will be more focused on this type of package. So now let me speak a little bit about RF packaging and why system in package technology is being adopted. So with the rise of 5G, cellular frequency bands have increased considerably, requiring innovative solutions for packaging front-end modules for smartphones and other 5G enabled devices. So the various RF active and passive devices can be actually included in a mobile device, either as a discrete component or as a system in package. For discrete type, the typical package types are wafer level packaging, QFN, and SOIC. And well, a single die is cost efficient for components like tuners or discrete filters. But if we speak about high-end smartphones, for instance, system in package is cost efficient for this type of technology, of course, and is preferred for performance efficiency, for miniaturization, and other reasons that I will address. So here, the three main types of system in package used for RF mobile applications are LGA, BGA single side, and BGA double side assembly. So the types of mobile handset RF applications that we'll be focusing on and that we are identifying are front-end modules, power amplifier modules, antenna in package, and Wi-Fi and Bluetooth modules. And as we can see here, the main suppliers of system in package for RF mobile are Qorvo, Qualcomm, Broadcom, Murata, and Skyworks. So before 2018, LGA system in package were mostly used in the RF industry. But BGA has ever since been widely adopted, taking some market shares from the LGA type. And this is also thanks to the development of double-side packaging, which is enabled by the BGA type. And as I said before, system in packages can use a combination of different packaging technologies and also different types of interconnections. So the most typical ones, as I mentioned, are the flip chip and wire bonding interconnection types, which are widely used for power amplifiers, filters, and switches. But we can also have other interconnection types in a system in package, such as TSVs with RDLs and flip chip for filters, for example, or RDL or UBM in the form of a wafer level chip scale package for filters, switches, and IPDs. So in the case of flip chip interconnection, either solder bumps, copper pillars, or silver bumps can also be applied. And when it comes to the configuration, both single-sided or double-sided solutions are available, depending on several factors like the functional integration requirements, number of components, and form factor requirements. Now, what are the main reasons to adopt system in package for RF packaging in mobile? So there are many reasons that we can consider why system in package is being chosen, especially for more high-end applications and high-end smartphones, instead of just placing discrete components in the PCB. So on one side, the adoption of system in package allows designers to mix and match IC technologies using different technology nodes, for example, and this way they can optimize performance of each individual functional block and reduce costs. So fully integrated system in package solutions can enable these designers to implement additional functionalities in the whole system, like Bluetooth, camera modules, and it takes a minimal design effort when comparing to doing several different packages instead of putting everything in a system. At the same time, compared to an SoC, in a system in package, different RF components can be fabricated at different nodes. So not everything needs to be at a very advanced node, and this can greatly reduce cost and time to market. And you can also have different fabs and different suppliers doing the different packages, and then you'll have someone who's doing the assembly. Then in terms of motherboard complexity, so by migrating the signal routing to the package substrates, so you'll be reducing the complexity of the motherboard and simplifying the product design, because you'll have several packages. So the most typical ones, as I said, flip chip or wire bonded, but you can also have some wafer level packages on top of IC substrates instead of connecting them directly to the PCB. So the complexity goes to the package substrate and not to the PCB. And then in terms of performance, of course, you can achieve better performance because your active and passive devices are brought closer together. So you have shorter line length, lower losses, higher signal integrity, and also reduced power consumption. And then, as I mentioned, this optimized system in package solution, for many reasons, they end up resulting in an overall cost reduction for the system. And then, and I think this is actually one of the main drivers, is the small form factor and the fact that you can really achieve a miniaturization of the whole system by placing everything together in a system in package instead of integrating different discrete packages in a motherboard. And then in terms of reliability, it's actually possible to achieve a better solder joint reliability compared to the discrete, which are assembled in a board, because the SIPs are all molded in the same package, which alleviates stress in the joints. So in some, flip chip and system in package solutions will become more popular as 5G moves forward. And now let me show you this roadmap, which concerns 5G packaging roadmap. So with the evolution of mobile network generations, new innovative solutions for the packaging of RF modules have come up to fulfill its requirements. We saw an evolution of discrete packages to system in package, starting with single-sided LGA SiP, then migrating to BGA, single-sided and double-sided system in package solutions. So over time, there's also the need to increase performance. And this has driven many innovations in the packaging, including in the materials to find new low-loss materials, EMI shielding solutions and enhancements, and other things that I'll bring up later. And so more recently, with the adoption of 5G, all of this needs to be improved. And so these enhancements in the package are needed. And for example, we have antenna in package becoming a huge trend. And this is just one of the things that we've been seeing integrated in high-end smartphones, for example, and will keep being adopted in the future. And as we might transit to 6G, for instance, we expect that more enhancements will be made in terms of materials. We expect heterogeneous integration of more components and thermal management and optical interconnection solutions to come up. So some of the key innovations that are included in this 5G RF system in package technology toolbox as I mentioned, the heterogeneous integration of different components with the use of compound semiconductors, for example, use of different technology nodes that can be produced by different fabs. We have the double-side assembly for more integration and lower footprint. We have EMI shielding solutions, conformal and compartmental solutions being developed by OSATs and other companies. We can have the embedded of active and passive dies in the IC substrate, which also requires more complexity in the process itself, but it's something that it can really be good for the miniaturization of the whole system and to bring the whole active and passive dies closer together. And then you should have dual mold or partial molds, the use of thinner substrates, for example, coreless substrates. So there's also a drive to improve complexity in the IC substrate side. And of course, the addition of more small passive components into the system in package itself. Then let me speak a little bit more about the antenna system in package. As I mentioned, this AIP adoption is a huge trend for 5G RF system in package. So in this case, instead of placing the antenna as a separate component, the goal is to integrate the RF transceiver and the antenna into the same package, which will originate shorter interconnections, a simplified design, and miniaturization. Of course, this brings several advantages, such as improved signal integrity with reduced signal attenuation, addresses the range and propagation challenges that occur at higher frequencies. It gives a greater design flexibility in terms of product development, faster time to market, and viability for 5G or IoT applications that require smaller package footprints. And well, here I bring some examples of the evolution of RF front-end module SiP packages provided by Broadcom and that are included in different versions of iPhones, Apple smartphones. So of course, one of the drivers is to attain a smaller footprint. And we can see that in the 2020 version of the iPhone, the system in package is 44% smaller than its initial version. And this is enabled by EMI shielding, flip chip technology being brought up, and double-side molding as well. So actually this double-side BGA packaging technology is allowing for higher component density with a new type of internal shielding and isolation of critical components using the PCB substrate. Then let me show you some market forecasts that have been extracted from Yole's Advanced Packaging Market Monitor. So here we are only focusing on RF system in package handset applications, including the front-end modules, the power amplifier modules, the connectivity modules, and the millimeter wave antenna in package. So what we see here is a stable but healthy growth in terms of units, driven by further advancement of system in package for 4G smartphones, and also the growing adoption of 5G smartphones. And in this 5G, system in package is, of course, a big trend. So over the forecast period of 2021 to 2027, the system in package revenue is expected to grow at a 3.2% CAGR from $3.5 billion to $4.2 billion. And this is, of course, driven by wireless and connectivity demands in 4G and 5G smartphones. So in terms of volume, we see that SiP package shipment is growing also at a 3.2% CAGR from 9.2 billion units to 11.1 billion units, with the highest CAGR of 12.3% belonging to antenna in package and millimeter wave front-end modules, as the adoption of the technology has just started. So millimeter wave front-end modules connected to a passive antenna is the approach currently used by Apple, as the larger antenna provides better gain and has a better radio link budget. And the front-end module system in package growth is also associated with integrating RF components such as switches and filters. And this module type is increasingly being used in flagship or mid-tier smartphones. Then power amplifier module system in package used to be restricted to 2G radio, and numbers decreased following the phasing out of 2G. But however, more high-end phones now have a 2G radio integrated, and this segment has also started to increase again following the introduction of 5G. And when it comes to Wi-Fi and Bluetooth connectivity modules, we see that incremental addition of antennas is needed to support 5G sub-6 GHz bands. So the Wi-Fi and Bluetooth system in package module approach is preeminent in the flagship segment. Then when it comes to the market shares, top RF handset SIP assembly suppliers are AZ, Murata, Amcor, Inari, Qorvo, Skyworks, Huatian, and JSET, and these actually together take more than 90% of the market shares. And from the system in package supplier perspective, the ability to package the RF system in package at the fastest time to market will be the key breakout with the advancement of 5G infrastructure, further propelling this RF system in package growth. Now, speaking a little bit about the supply chain, it involves several different business models, and it can work in many different ways depending on the product and on customer requirements. On one side, there are the substrate manufacturers, which provide laminated IC substrates. This will be later used for the assembly of different packages to form a system in package, and the assembly will be done by an OSAT or an IDM typically. So top IC substrate suppliers are actually located mostly in Taiwan, Japan, and South Korea. When it comes to the packaging, assembly, and testing, the main suppliers here are OSATs like AZ, Amcor, JSET, and others. Then we have some IDMs like Murata, TI, Skyworks, Qorvo, Infineon, and others, which can also be doing the design and the system design and the chip design, but they also have some backend capabilities, so they also can do the packaging and assembly of some of these components. And then we can also have EMS business model, for example, USE, which now is part of AZ Group, is an EMS company who also does some system in packaging. So they don't produce individual packages, but they do the system in package assembly at the system level. And then we have fabless and design houses and even IDMs, which have the capability of designing the products, and they can either produce it internally or outsource it to other foundries or IDMs or OSATs, IDMs and OSATs for the backend part, of course. And then also in the supply chain, there are the end product system makers, these being the ones that sell the final product. Now I'll give you two examples of OSATs which are strongly investing in advanced SiP packaging technology. These will be AZ and Amcor. So first, starting with AZ, which together with SPIL is #1 in the overall OSAT revenue ranking, and also #1 for the system in package supply. So this year, AZ Group introduced a new platform, which is called VI-Pack, and comprises different advanced packaging solutions, mainly focused on fan-out and 2.5D and 3D types of technologies. And actually, most of these solutions are meant to be system in package solutions because they are meant to integrate different packages or different dies in the same system, which will do different functions. So you'll have an heterogeneous integration trend coming here. And one of the goals of this VI-Pack platform is for AZ to provide a flexible service to its customers, where it's possible to mix and match different package technologies and different package architectures in the same system. So then we have the example of Amcor. Amcor also has a diversified portfolio regarding SiP capabilities, and this includes flip chip EGA, system in package, single-sided or double-sided system in package, fan-out, embedded die technology, wire bonding, etc. So I guess they keep investing a lot in this advanced SiP packaging business. They are now expanding their capacity towards Vietnam, where I think in 2023 this building will be ready, and it will be mainly focused in advanced SiP. So I guess Amcor is seeing a big part of the revenues coming from system in package activities. So they are trying to improve their product portfolio as well. And well, finally, we have come to our conclusions. So we can see that on one side, the 5G penetration in mobile and consumer market is driving the adoption of system in package, in connectivity and RF. 5G requires higher performance with challenging electrical, thermal, and mechanical requirements for a longer operational battery life. Then flip chip and wire bonding solutions can enable miniaturization and semiconductor integration to enhance system performance by increasing the bandwidth, lowering power consumption, and enabling increased functionality. And there are a couple of things that are also trending in RF packaging. Some examples are antenna in package, and also double-sided SiP is also trended, being the main driver, the miniaturization, and to be able to have shorter interconnections between different dies in the same system. So we also have seen that RF handset system in package revenue is forecast to reach $4.2 billion by 2027 from $3.5 billion in 2021, with a 3.2% CAGR. Then we have companies like AZ, Amkor, and Murata, which are market leaders, and in this RF system in package for mobile handsets. And actually, Apple remains as a key customer and drivers for the growth of these OSAT revenues, as they are one of the key companies for high-end smartphones. And we also see that OSATs, I gave examples like Amkor and AZ, but overall the highest ranked OSATs are continuing to invest in system in package infrastructure for components, SMT attached chip shooters, wire bond capabilities, partial molding, compression molding capabilities, and conformal and compartmental shielding capabilities as well. So I just show you here this slide with some of the reports that we have at Yole Intelligence Portfolio, and in many of these you can find some of the information that I've spoken today. And well, thank you very much for listening.
Thank you, Gabriela, for the very nice presentation. I see there is already a question in the chat. Paul van Dijk asks, first of all, says, great presentation. How do you see the impact of current economic crisis in your forecast NCS plus AGSR as presented? Do you see reshoring to EU from Vietnam?
I'm trying to understand what these CS and AGSR are. But speaking about the current economic crisis in the forecast, so we do know that the demand for certain devices such as the smartphones, but mainly in the PC segment like laptops, desktops, there's a softening in demand. So you see many companies, for example, like Intel, presenting results that are not so good in the last 2 quarters of this year. And we expect to have a flattish 2023 for the semiconductor market and for the packaging market as well. But actually, when it comes to the most advanced packaging technologies and most advanced system in package technologies, there is a growing demand. So the growth will always be positive. It can be flattish than previous years, but it will be positive. And one of the big things that is important here for system in package and RF system in package is that although the smartphone demand can be softening, the 5G smartphone demand is increasing. So we will see further adoption of system in packaging in 5G and increase of silicon content as well. So I think our forecasts, we see a growth, and I think that we will continue to be positive. We know that in the semiconductor industry, there are some current economic crises, yes, but for this advanced packaging, we continue to be a bit positive. And when it comes to the Vietnam part, reshoring to Europe from Vietnam, I think that Amkor's strategy can be to enlarge its capacity in different continents and in different places. So Vietnam, I think it can be a key place for them to have a system in package capability, but in Europe, they are actually investing a lot, but more in the automotive business, but also with some system in package, of course. So yeah, I think they are just trying to diversify their capacity all over the world in different locations.
Yes, thank you. I see a question from one of our moderators, from Marco Koeling. Please go ahead.
Thanks, Gabriela. So your roadmaps show a continuous evolution of the electrical components and the corresponding package technology. I'm kind of thinking, do you foresee at any point in time that also maybe optical or electro-optical components are introduced in 5G and 6G smartphone technology?
Yes, I think that will be a trend in the future, and probably there's already some R&D going around that. And I think in the future, I think we see companies that already speak about projects on that. And we actually receive lots of questions about the optoelectronics incorporation in advanced packaging. So I believe that will be a trend in the future, yes.
Can you maybe indicate a little bit in which kind of components and what time frame are you thinking of?
Well, for which type of components, I guess it will start maybe not so much in the mobile part, but more in the networking, 5G infrastructure. And in terms of time frame, for the most advanced technologies like 2.5D, 3D configurations, probably in the next 3 to 5 years.
Okay, thank you very much.
I have a question myself about antenna in package. It's already quite for several years one of the main trends that it's mentioned in the RF field. And I'm curious, what is at the moment and in your forecast the main application driver for the adoption for antenna in package?
So here, the main adoption in this forecast is, if you're talking about application, so is the smartphone and is the increased adoption of 5G smartphones. That's the biggest driver for this antenna in package adoption.
Thank you.
Sure.
I think there is an additional question in the Q&A. If we have time, Ralph Leclerc actually is asking if automotive help will help to trigger this segment.
I guess if we are speaking about RF antenna in package, in automotive, we do see some automotive radar, for example, using fan-out technology and incorporating an antenna in package with the automotive, with the RF transceiver. But this is using fan-out technology, not flip chip and wire bonding. But I think that's something that is going to grow in the future as well.
Okay. If there are no more questions coming in the chat, then with this presentation from Gabriela, we would like to conclude this RF session on the forum. We will continue later this afternoon with a power session.
Hello again, everyone. I think we have newcomers for the power packaging session. Before we start this session, I would like to add a word about the RF packaging. One speaker was missing, Jérôme Serrand from GSR. He was sick, but if you have interest in this presentation that was related to 5G and RF materials, that will be available in the proceedings that will be distributed afterwards. So now we can start the power packaging session. That will be moderated by Asger Smith and myself. So the stage is yours, Asger.
Okay, so good afternoon for this last session about power packaging. So we have a very nice lineup this afternoon, starting with Cristina Di Marino from Virginia Tech. And then we will continue more commercial discussion with Victor Villanis. And finally, we will look more at the market in general with Amin Alouche. So to start off, I would like to introduce Cristina Di Marino. So she will talk about packaging and integration of advanced power semiconductors. Cristina, the floor is yours.
Well, thank you for the introduction. Good afternoon. I will be, so my name is Cristina Di Marino. I'm an assistant professor at Virginia Tech, and I work in the Center for Power Electronic Systems, CPES, and work on power electronics, packaging and integration for wide bandgap power semiconductors. Power electronics are really fundamental for the transportation electrification trend that we're seeing from electric vehicles to electric ships and more electric and hopefully eventually all electric aircrafts to help to decarbonize our transportation infrastructure. And so the power electronics are really playing a major role in this electrified transportation trend. Our power electronics really start with our power semiconductor devices that really control that electrical energy flow and power conversion. And then what we'll discuss today in detail is the packaging of those power semiconductor devices, specifically the multi-chip power modules. And then those modules are assembled together, those power electronic modules are then assembled together with inductors, capacitors, and the control, driving, sensing, and protection circuitry to create our power electronic converters that provide the electrical energy conversion. This could be used for both AC and DC. And so then these help us to interface the various loads and sources that we have in our electrical systems. And I'm showing here an example of, electric aircraft, but you can also imagine that we have similar systems in electric vehicles as well as in the grid. Especially now with having more distributed renewable energy sources and changing loads as well, such as for EV fast charging, that's requiring more and more power electronics at the grid scale as well. And I'll touch on kind of some power electronic packages for a variety of applications. Before I get into the technical details, I did want to start with a brief overview of kind of conventional power module packaging. So this is showing a cross-section of a kind of conventional silicon power module. So the red rectangles here are the power silicon devices. Those are then typically bonded using solder to a ceramic copper substrate. And ceramic is commonly used in power electronics because of the good thermal performance and good electrical insulation. But because ceramic is brittle, that's going to limit the overall footprint area of these substrates and limit the amount of copper that you can put, that you can metallize onto the substrates. And because these are power applications, these copper layers are going to be quite thick, on the order of several hundred micron. So the die are bonded to the substrates. The top is patterned to provide the electrical distribution. And then the most common interconnect is wire bonds, typically wedge bonding, heavy gauge aluminum wedge bonding for power electronic applications. These ceramic substrates are then bonded, typically using solder. This is typically a large area soldering process to a base plate that provides the heat spreading as well as mechanical support for the package. Then you've got terminals that typically come out the top of the package and are screw terminals. So they mount to the bus bar and rest of the converter using screw terminals typically. And then the package is typically encapsulated using, for example, a silicone gel, though overmolding is also becoming increasing in popularity for power modules as well. And then for the thermal management, all of the heat is generally brought down through this bottom portion of the power module. So from the drain contact or base bottom contact of the power semiconductors, and then through all of these interfaces to the heatsink. And so the power module is interfaced to the heatsink using a thermal interface material. And for transportation applications, instead of a finned heatsink, you might see more of a liquid cold plate approach to the cooling. And so while this approach for this power module packaging that I showed here, all these technologies are suitable for kind of lower speed, lower power densities, and lower voltages for silicon power semiconductor devices, we kind of have noticed that they are not really sufficient to extract the full benefits of wide bandgap power semiconductors, which I'll talk about now on the next slide. So this is showing here some of the critical material properties for power semiconductor devices. So these are the material properties for silicon, which is still the primary semiconductor material used in power electronics today. And then shown in purple here are the properties for gallium nitride. And then shown here are the properties for silicon carbide. And so what these material properties really translates to from a power electronics perspective is lower conduction losses while these transistors are conducting current. Because again, this is for power electronics. So the conducting currents could be on the order of tens or hundreds or thousands of amps. And so the conduction losses are really critical for this application. Also the blocking voltage capability. So by moving to these wide bandgap devices, because of the higher critical electric field strength and because of the wider bandgap, they can now support larger voltages in the tens of kilovolts range. And also they can operate with stable performance and while maintaining high efficiency at higher temperatures compared to silicon. And then because of the higher saturation, velocity, and electromobility, they can also switch much faster relative to silicon as well. So then what this translates to at the converter and system level is greater power efficiency, greater power density, so we can now process much larger amount of power over a smaller volume and hopefully with lighter weight. Improved reliability of the power converter, which is really critical for transportation applications, and also reducing costs. So these are the potential benefits of these wide bandgap power semiconductors and why there's been a lot of research and effort involved surrounding these gallium nitride and silicon carbide devices in the last few decades. And so I'll briefly kind of touch on how we've been kind of evolving from the conventional power module structure that I showed on the previous slide into kind of power module technologies that could better kind of extract these benefits of wide bandgap devices. So the first is because of these lower conduction losses, we're now trying to process higher currents through these power semiconductor devices. So we've been looking in particular at alternate substrates and alternate interconnect technologies. This is showing here, instead of using a ceramic-based substrate material, using an insulating metal substrate based on polyamide, which is now a flexible material, but still has good dielectric strength. And you can now get much thicker copper bonded to the top portion to conduct higher currents and also have more better heat spreading near the power semiconductor devices, because these advanced wide bandgap materials have much higher current densities, and therefore the heat flux is much higher, which I'll talk more about on the following slide. They can also be used to bond dissimilar materials. So on the top, you could bond copper, and on the bottom, you could bond aluminum for reducing weight. And so this could allow you to also reduce the number of thermal interfaces and eliminate the separate base plate that I mentioned on the previous slide. And you can imagine you could also integrate cooling channels and things like that into this substrate. We've also been exploring technologies for higher voltage packaging for these power semiconductor devices, so upwards of 10 kilovolt, and looking at ways that we can grade the electric field strength inside the package as well as outside the package to maintain very high power density, so a very compact package, while being able to block high voltage. We've also been exploring materials that can operate reliably at higher temperatures. So conventional power module packages are limited to around 150 degrees Celsius. With silicon carbide and other wide bandgap materials, there's the possibility to operate reliably and with higher efficiency at higher temperatures. And so we're exploring encapsulation and other material options that can operate at higher temperatures, such as nanosilver sintering. And then we're also looking at new integration approaches. So with the fast switching speed of these wide bandgap devices, we need to be very cognizant of parasitic inductances and parasitic capacitances that could cause undesired ringing and current and voltage overshoots that could damage the power semiconductor devices. So having new forms of integration and really coming up with more compact package solutions and lower inductance interconnects are really critical for achieving and realizing this fast switching speed. Here is showing an example of a package where the silicon carbide MOSFETs are actually embedded inside the printed circuit board together with the gate driver so that we can get very low parasitic inductances and achieve very fast switching speeds. So that kind of brings me into the challenges associated with packaging these wide bandgap devices. So unfortunately, those benefits that I showed on the previous slide are not free. So the higher current densities that are achieved with these gallium nitride and silicon carbide devices result in much higher heat flux, which is very challenging to cool using the conventional packaging and cooling strategies. And so we're seeing trends, and I'll talk more about this later in the presentation, seeing trends for reducing the number of thermal interfaces and the number of layers overall in the package structure to get the coolant as close as possible to the semiconductor devices, and going towards more targeted cooling strategies such as this jet impingement cooling system that I'm showing here that's directly targeting the power semiconductor device locations for more efficient heat extraction. We're also working on ways that we can better control the electric fields so that we can get high partial discharge inception voltage so that we can operate these packages at these higher voltages. In terms of operating at higher temperature, that's going to result in lower reliability for the package materials. And so we're looking at materials such as nanosilver sintering which has very good high temperature capability to see kind of how we can extend the reliability of our package to higher temperatures. And so this is an example of a sintered silver bond for a large area to replace that solder joint between the direct bonded copper substrate and the base plate. And it survived over 1,000 cycles over an extreme temperature range. And then finally, with the faster switching speeds and the higher switching frequencies, that's resulting in more electromagnetic interference, which needs to be addressed throughout the design of the converter, really designing for EMI kind of at every step in the converter design process. And in particular, what we've been exploring as well is how can we design the package to also mitigate the amount of conducted and radiated EMI that leaves the package, both common mode and differential mode, through integrated screening, shielding, and through balancing of the impedances to minimize the electromagnetic interference. So next, I'd like to just touch on some of the approaches that have been taken, and particularly in the electric vehicle industry, to address the thermal challenges associated with these advanced power semiconductor devices. So I'll kind of start with in the early 2000s, kind of the state-of-the-art packages that were used then in the early electric vehicles. So they were using silicon IGBT devices, so conventional slower switching devices mounted to a direct bonded aluminum substrate, and then that's soldered to a base plate, and then that is then bonded to a heatsink. So a very conventional type of packaging approach overall. And then in around 2010, with the Chevrolet Volt, we started seeing some more advanced packaging technologies being used, such as flip chip soldering for the power semiconductor devices, and elimination of the base plate, so removing one of the thermal interface layers, and then using instead direct substrate cooling, so directly cooling the other side of the ceramic, and also using double-sided cooling, which helps to reduce the thermal resistance by about 30%. And then in 2017, Tesla incorporated silver sintering into their packages, and instead of using wire bonds, used copper clips. They also eliminated the base plate, and then for their cooling, instead of double-sided cooling, they did single-sided, but with a pin-fin cold plate to enhance the surface area. And then 2018 with the Audi e-tron, seeing again continuing on that trend of eliminating the base plate using pin fin cold plate, as you can see here on both the top and bottom, to have double-sided cooling. And so overall, the trends that we've been seeing in this kind of very competitive market are a reduction in the number of interfaces and layers in the power semiconductor package, particularly removing the base plate, decreasing the distance between the semiconductor device and the cooling system, again, by reducing those number of interfaces, which also helps improve reliability, and increasing the surface area, either through pin fins or double-sided cooling, because again, these semiconductor devices are becoming smaller and smaller while they're being able to process higher powers and becoming more efficient. So the current densities are increasing, and so we need to increase that surface area either by going to double-sided cooling or through pin fins in order to extract the heat from the semiconductor devices. And next, I'll show some of the work we've been doing with AT&S on PCB embedding of silicon carbide devices. This is also for an EV application, though the modules I was showing on the previous slide were for an EV inverter. And so they were realizing that you could get significant performance benefits of your EV by using the advanced packaging strategies. And here we're looking at an EV onboard charger. And how we can get better power density by using advanced packaging techniques. So inside this 4-layer PCB, the silicon carbide MOSFETs, 1.2 kilovolt, are embedded into the PCB. The total PCB thickness is only about 0.1 centimeters in total. And the gate driver is integrated together to create very low power loop inductance and gate loop inductances, which result in very clean switching waveforms with very limited voltage overshoots. And also we incorporated double-sided cooling, which I'll show more about on the next slide. And so we were able to put multiple of these half-bridge modules together into a 22 kilowatt 3-phase AC-DC converter for an onboard charger application. And achieve a peak efficiency of 98%, over 98%. So in this slide, I'm just showing the measured thermal resistances for a conventional TO247 package, which is still widely used in automotive applications today, as well as a number of other applications, and then comparatively showing kind of the measurements from the PCB embedded package. So looking at kind of the drain side thermal resistance. So as I mentioned, the device is double-side cooled. So this is looking at a kind of cartoon cross-section of the PCB embedded module, where we have here the silicon carbide MOSFET. And then through the bottom drain contact, we have a much lower thermal resistance compared to the TO247 package. If we look at the thermal resistance through the top, through the source side of the device, then we see the thermal resistance is going to be quite a bit higher. And that's because we don't have as much surface area and because we have microvias that are contacting those source pads on the top, rather than the drain, which is just one large contact. And then if we combine these two to have double-sided cooling, both through the drain and source side of the package, then we get around a 57% lower thermal resistance compared to a TO247 package. We then also performed switching tests as well. So we operated a TO247 package and the PCB embedded package in the same converter using the same silicon carbide devices. And because of the lower parasitic inductances and resistances of the package, we're able to achieve over 1% higher efficiency at light load when the switching frequency is higher compared to a TO247 package, which is a significant improvement. And then these are showing the successful operation under 3-phase 22 kilowatt for the AC-DC converter from 480 volt AC to 800 volt DC. So next I want to touch on a little bit of a different application. So moving to kind of the higher voltage end of the spectrum, showing really what's possible with silicon carbide and wide bandgap devices in general. So with these wide bandgap devices, we can get 10,000 volt silicon carbide MOSFETs, which is not possible with silicon. So with silicon, to get to this type of voltage level, you need to go to a thyristor-based solution, which has slower switching speed and less controllability. So this is really a unique application area that wide bandgap devices offer. And so what we've done is develop a really compact package that has both field grading techniques to minimize the electric fields to be able to support these types of voltages, while also being compact enough that we can get low stray inductances, because these MOSFETs still have very fast switching speeds, switching on the order of 200 volt per nanosecond or higher. And so maintaining that really compact size and short interconnect distances is also very critical. And so we went with a wire bondless design, which I'll show more about later, that uses molybdenum post interconnects to create a kind of quasi 3D type power flow compared to the wire bonded approach. And then we also co-designed the module together with the bus bar and gate driver interface to really minimize the parasitic inductances and also carefully control the fields, not just inside the package, but also outside the package where you're going to have air as the insulator. And so these are just showing some of the high voltage testing experiments that we've run. And we're able to, even though this is a very compact package, it's only about 8 by 7 centimeters square. And the terminal spacing for 10 kilovolts about just under 1 centimeter. So it's very, very close together. We're still able to achieve very high partial discharge inception voltage of over 16 kilovolt. And then we have now been expanding that package to get more power throughput through these devices. So for power applications, it's really critical to push as much current through the semiconductors as you can to get the most power density benefit. However, when you do that, the heat dissipation is going to increase. So the better your thermal management system, the more current you can and power, therefore you can push through your module. So we have been exploring double-sided cooling for these 10,000 volt silicon carbide MOSFET modules. So this is the first, as far as we're aware, first double-side cooled 10 kilovolt module that's been demonstrated. So here in teal, these are the silicon carbide MOSFET die. And then these bumps that are on top of the silicon carbide MOSFET, those are the molybdenum posts. Molybdenum is chosen because of the coefficient of thermal expansion, which is matched to the silicon carbide. And we have 2 silicon carbide devices bonded to an upper substrate and 2 bonded to the lower, and that's to minimize the amount of thermal coupling so that we can get even better thermal performance. And then this is showing a 3D printed jet impingement cooler that's integrated into the module housing. And we've eliminated the base plate and have that really targeted cooling performance that I mentioned on the previous slides. And also able to maintain low inductance at the same time because of the very compact nature. So you have these kind of key trade-offs between the inductance, which requires very compact size and very small distances, but at the same time, when you have very close proximity of the different components, then you have poor thermal, poor heat dissipation. So there's a constant trade-off that we're playing with here in power modules. And then kind of my last slide, I wanted to touch on the potentials and challenges for emerging semiconductor materials and devices. So in particular, the ultra wide bandgap devices, such as gallium oxide, for example. There are other materials as well that are also being explored. Gallium oxide here I wanted to touch on because it's very promising from a cost perspective. Because of the melt regrowth process, it has the capability to be low cost in very high volume applications. Because of the higher critical electric field strength and wider bandgap, it also has the potential to be used for even higher voltage devices. So we could get even higher voltage, faster switching devices, which could be very beneficial for grid level applications, as well as for distribution on electric ships and other larger systems. Because in general, we're seeing a trend in our power electronics applications towards higher voltage in order to be able to process more power, but maintain high efficiency. Another key benefit of gallium oxide is it has phenomenal stability at high temperatures and also has a very good figure of merit at cryogenic temperatures, which is also of interest for some electric transportation applications. However, a major challenge for gallium oxide for power applications in particular is the very low thermal conductivity, especially relative to even silicon. So that's kind of a major focus for our work in the recent couple of years. So in particular, we've been working on developing an electrothermal device package co-design that accounts for the device physics and the device self-heating phenomena, as well as the thermal nodes and thermal resistances associated with the package. And then we've also been looking at, asking ourselves, okay, so conventional modules are limited to around 150 degrees Celsius because of the limitations of the device. Because these wide bandgap and ultra wide bandgap devices have higher efficiency, can maintain high efficiency at higher temperatures, we could ask ourselves if that 150 degrees C limitation is still necessary. So we're also seeing about operating these gallium oxide devices at higher temperatures, say at around 300 degrees C, and we're exploring non-polymer based encapsulants for that operation. And from our analyses, we've seen that if you can topside cool the gallium oxide devices, then you can significantly overcome these negative consequences associated with the low thermal conductivity and can potentially get good performance out of the gallium oxide devices. And so we're working right now on actually prototyping the first topside cooled gallium oxide power module, and we'll also be operating this at higher temperatures as well. So just to wrap up, so the wide bandgap devices overall offer a lot of great promise and benefits for future electrification, transportation, and also grid level applications. However, some limitations to the full utilization of these wide bandgap and emerging ultra wide bandgap devices are really the heat dissipation, the electromagnetic interference, and the voltage insulation. There are other limitations as well from the converter perspective that would need to be addressed to be able to operate under these conditions. From a thermal perspective, we're seeing more trends towards more direct and double-side cooling approaches, as well as pin fins to really increase the surface area. For EMI, we're trying to design for electromagnetic compatibility from the package level all the way to the converter level. For insulation, we're exploring new field grading materials that can help to smooth those high electric field points, and also trying to use multi-layer substrates and field plates to better grade the potentials and the fields in the inside and outside of the package. And kind of some, I think, critical pieces for really overcoming the present limitations are going to be improved design tools for these multi-physics trade-offs, new materials, and cooling strategies in particular. So thank you all for your time. I'd be happy to answer any questions.
Yes, again, thank you very much for this impressive presentation. I think we have one question from the Q&A. So, which is, which market segment needs more than 800 kilohertz?
So it's more based on the converter benefits that you get from going to higher switching frequency. So for power applications, when you increase the switching frequency, that means that the filter components or the passive components in the converter can decrease. So we can have less inductance and less capacitance, which then drastically reduces the volume and improves the power density of the converter. And it can also be, it could also be beneficial for the power quality to some extent as well. So it has a number of potential benefits at the converter level.
Good. And also a question from my side. So indeed, going to higher temperatures or operating at higher temperatures is very interesting. And how far does the decrease in thermal conductivity of silicon carbide or other semiconductors start playing a role, or do you compensate this by making the devices thinner? So
yeah, that's a great question. So what we've done some studies, and there have been other studies also reported in the literature that show that the thermal conductivity of the power semiconductor devices is not very critical. It's not the bottleneck in the thermal management, generally speaking, for power applications. Generally, it's more the thermal management system, such as the really convective heat transfer coefficient that thermal resistance tends to dominate. And there have been some studies that show that, a thermal resistance any higher than silicon, you see really limited return on your investment for a given package. And the silicon carbide devices have very high thermal conductivity, higher than silicon, and are also thinner. So their thermal resistance is really negligible. And even that of silicon is fairly negligible compared to the other thermal resistances in the network overall.
Yeah. Finally, so you were talking about nano silver sintering. Are you then referring to pressure or pressureless sintering in your case?
We've explored both for smaller areas, which for us is roughly 1 by 1 centimeter squared, or maybe up to 2 by 2 centimeters squared. We can get away with pressureless sintering for certain materials. For larger areas, such as bonding, let's say a substrate to a base plate, then that might be like several centimeters by several centimeters. Then we would want to apply some pressure up to a few megapascal generally. Though there are other materials that require pressure. So it kind of depends on the silver material that you're using. And if you apply pressure, the benefit is that the sintering process is shorter. It can be a few minutes on the order of what you would have for soldering. If you go with a pressureless approach, you need to sinter for a longer amount of time.
You have timed, Emily, do we still have time for one question?
Yes, yes.
Yeah, Sebastian, had a question?
Yeah, with regard to the graph you showed on gallium nitride, does it has a place to play in the future? And gallium nitride on silicon carbide substrate, maybe?
That's an ongoing question. I think in general, what we're seeing is more interest in GaN on silicon because of the low cost benefits, because of the cost benefits overall. And the markets where gallium nitride is really seen as kind of standing out compared to silicon or compared to silicon carbide, those are really going to be more cost sensitive applications. So I think we're going to continue to see that trend. I think overall the thermal benefit that you get for GaN on silicon carbide is really minimal compared to the cost increase. So I don't know that we're going to see much of a trend there. There's also some of that being explored for gallium oxide on diamond or silicon carbide to improve its thermal conductivity. And it's just hard to justify the cost because versus the thermal improvement that you get.
Thank you.
So again, I would like to thank you, Christina, for this impressive presentation. And I would like to continue the session with the next speaker, Victor Iliadis. He is the director of Power America Consortium, and he will present about accelerating silicon carbide power electronics commercialization. So, Victor, the floor is yours.
Thank you very much for the invitation to be here, and let me know if you can see my screen.
Definitely. Yeah.
Okay, perfect. Thank you. So what I'm going to do is I'm going to take a step back and talk about silicon carbide power electronics commercialization, where we are, some of the barriers, and then talk about some examples of packaging and module work that we've done. Christina gave an excellent presentation on the issues with packaging and silicon carbide modules and some of the top work being done in this area. So first, I wanted to point out that, as you get to the latest node, it becomes increasingly more expensive. And let me get my laser pointer. And you can see that when you get to the 5 nanometers, Intel, TSMC, and Samsung were the only semiconductor companies that were able to fabricate. And then moving to nodes even beyond that, it's really only Samsung and TSMC. And again, it takes billions of dollars in tools and investments to work on the latest node. However, there are a lot of opportunities in memory and logic, IO2, artificial intelligence, 5G, and power semiconductors, where you can use mature fabs to fabricate those devices. So that really brings the cost of fabrication down. Now, when we talk about power devices, this is an example of a wafer that has silicon carbide devices. This was processed back in 2004, 2005, and you can see this is a fully processed silicon carbide wafer. It's tested, and then we dice the parts, and we did this makeshift package with aluminum wire bonds just to be able to look at the capability of the semiconductor. And you can see that it's capable of doing, up, 50 amps or so, depending on of course, on the thermal dissipation capability of the package. And then it's capable of blocking high voltages. So in the area of this silicon carbide chip, if you were to do the latest logic, you would be able to get more than 1 billion transistors. So when it comes to power devices, they're monolithic and large area transistors. So Christina did an excellent job explaining this graph that shows the relative properties of silicon carbide, and GaN. But just very briefly, I'd like you to pay attention to the electric breakdown field of silicon carbide and GaN. It's 7 to 10 times higher than that of silicon. And also, please note that the band gap of silicon carbide and GaN is a lot higher, more than 3 times higher than that of silicon. And of course, silicon is the conventional semiconductor where the majority of power devices are being made today. And if you look at a typical power device, a vertical power device, there's a thick drift layer that holds the high voltage. So the thickness of that drift layer is inversely proportional to the critical electric field. If your critical electric field is 10 times higher, then you can have a device that will block the same voltage, but the thickness of that device will be 10 times smaller. And if you look at the device resistance of this thick layer that blocks the high voltage, it's inversely proportional to the third power of the critical electric field. So again, a critical electric field being 10 times higher, that can be 1,000 times smaller. So overall, the promise of silicon carbide and GaN devices, which has led to this phenomenal growth, is through the large band gap and critical electric field, you're able to make high voltage devices with thinner layers. So you reduce the conduction losses, and also the fact that you have a wide band gap means you can operate at higher temperatures with low leakage. And of course, the thinner layers with smaller specific on resistance means you have smaller form factor and you reduce the capacitance. And this is crucial because reduced capacitance means you can operate at higher frequencies very efficiently, and operating at higher frequencies reduces the size of passive components. And of course, particularly in the case of silicon carbide, you can see it's got a high thermal conductivity. So that means you can operate at higher temperatures with reduced cooling requirements. So you can reduce the heat sink and so on and so forth. So these are all compelling advantages that have led to significant growth. And I would like to briefly point out that if you look at the GaN devices that are on the market today, the commercial devices, they're all lateral devices. So you have the drain, source, and gate, and the breakdown voltage capability of the GaN device is based on the separation between gate and drain. So the larger breakdown voltage, the higher the separation, and also the insulating buffer layers have to be thicker and adjusted for high voltage. And these are kind of limitations when it comes to how far you can push a lateral device. Once you exceed a certain voltage, the drain to gate separation becomes large, and therefore you get fewer devices per wafer, which increases the cost. If you look at silicon carbide, however, all the devices are of vertical configuration. So the drain to gate separation that determines the high voltage is vertical. So as you go to higher voltages from 600 volts to 10 kV, really you're increasing the length of this layer and you're adjusting the doping optimal values, but you're not taking more space up on the wafer. So if you look at high voltage power devices, once you exceed 600, maybe 900 volts, it makes sense to go to a vertical configuration for devices made out of silicon carbide and GaN. So today, the power electronics engineer has a choice. He can do silicon carbide, or GaN, and the selection is based on the application specific requirements. What are your voltage requirements? How much current do you want to pass through the device? Density, how high a frequency do you need to be at in order to get a lot of power density, efficiency requirements, what are your temperature requirements, and cost considerations. So just very roughly speaking, silicon is extremely competitive, of course, from the low voltages, 15 to 650 volts. GaN is competitive from 100, the lateral GaN, of course, that I'm referring to that's commercially available, going all the way to maybe 900 volts, kind of pushing it. About 600 volts is the sweet spot. And of course, silicon carbide is extremely competitive at very high voltages. Silicon, as we all know, is reliable, rugged, it's cheap, and there is a device and circuit design legacy. People know how to basically make efficient silicon circuits. If you look at GaN, it can go to very high frequencies at reasonable cost, and that helps you reduce the passive components. And of course, silicon carbide, same situation. It's efficient, and it also operates at higher temperatures. And if you look at the 650 volt area, that's where you have the electric vehicle application, which is a massive application. They have a 400 volt battery and operate at need 650 volt devices to get overhead. And silicon, GaN, and silicon carbide are all very, very competitive in this range. Okay, so as I mentioned before, the wide bandgap silicon carbide and GaN system opportunity is when you have the higher power levels at high frequencies where silicon is inefficient. And that translates to a number of applications. At the higher voltage, you have HVDC, you have the AC transmission. And then, as you go a little lower in voltage, you have traction, motor drives, power supplies, a lot of automotive applications. So a very big market. And I wanted to point out that when it comes to silicon carbide and GaN technology, the efficiency can benefit from generation to transmission all the way out to consumption. So there are a lot of applications for silicon carbide and GaN, and there's a lot of improvement in efficiency that can take place by using these devices made out of these materials. So the biggest application, as you know, when you have a new device, a new material, new devices, you're always going to be initially very expensive. So you need one big killer application to get to volumes where you can reduce the cost, where you can go to economies of scale and reduce the cost. And for silicon carbide, that big application is the electric vehicle. In particular, you have the traction inverter, the DC converter, and the onboard charger. And as you know, Tesla inserted silicon carbide back in 2017, 2018, and all the automakers are moving in that direction because they want to basically exploit the benefits of efficiency that will allow them to get higher ranges. So this is the one big killer application for silicon carbide: commercial volume and reduction in cost due to economies of scale. And of course, we're now moving very fast from the 400 volt battery architecture to the 800 volt battery architecture in electric vehicles to get longer range, charge faster, and of course, cost reductions with a reduction in the number of cables when you go to higher voltages. And if you're going to do the 800 volt battery bus using 1200 volt devices, of course, to get some overhead, that would be silicon carbide. You can do a 2-level type of inverter. However, in the case of GaN, because the devices are rated at 600 volts, there are no commercially available devices at 1200 volt. Then to do the 800 volt bus for this battery application, using 600 volt device, you have to do a 3-level type of inverter configuration. So you double the number of devices. So competing for the traction inverter, silicon carbide with the 2 levels uses fewer devices, reduced control complexity. But of course, when you go to a 3-level architecture, you have less harmonic distortion. So there's a lot of competition there. Of course, the other thing that comes into play is the amount of current, right, that you can get through a device. And GaN being a lateral device, having this thin inversion layer where of course a lot of the heat is generated. That means that you're kind of limited in the amount of current. Of course, in the case of silicon carbide, you're also limited because the size of the device has to be such that you get high yields, right? And because of the defects, you're kind of limited in the area. So that's an area of competition. in the case of the onboard charger that requires lower power levels, so therefore the devices do not need to be of very, very high current capability, GaN has, of course, a huge advantage because it's able to operate efficiently at higher temperatures than those of at higher frequency than that of silicon carbide. So a lot of work is being done with wide bandgap insertion, power semiconductor insertion in automotive. And of course, this is a Yole conference, and of course, Yole has been doing excellent work in projecting the markets, and the 2027 projection for silicon carbide, 6.3 million. And note that 6.3 billion and 5 billion of that is in automotive. So automotive for silicon carbide is the one big application. And with respect to the different market that silicon carbide and GaN are projected to have by 2027, according to the Yole estimates, silicon carbide would reach 20% with GaN 7%. And you can see, of course, that silicon power devices, again, tend to be very powerful and a big portion of the market. So some people say that silicon is dead. It is not. You know, you have silicon carbide, and GaN, and each one of those semiconductors can be an excellent solution for specific applications and requirements. So they all coexist. Okay, so let's look at some of the issues with silicon carbide. The biggest one is the growth of the silicon carbide substrate. In the case of silicon, 1500 degrees, you have a necking from the molten silicon, so you get a very clean, low defect wafer. In the case of silicon carbide, it does not melt. It sublimes at temperatures of about 2300 degrees to 2500 degrees. And you need a seed layer in order to start the growth of your boule. So this is very labor intensive, and the length of the boule is a lot smaller than that of silicon. And of course, because it's a very hard semiconductor, when it comes to polishing and all the wafering process is more complex. So what does that mean? That means that about 45 to 65% of the silicon carbide device cost is coming from the wafer. So the substrate and the epi are 45 to 65% of the device cost. And that has led to a lot of vertical integration. All the manufacturers of silicon carbide want to have a steady supply and low-cost supply of silicon carbide substrates. So you see, for example, part of that vertical integration, STMicroelectronics acquired Norstel. If you look at II-VI, which was a substrate only supplier, it acquired Ascatron to do the epi, and it has licensed the General Electric MOSFET process to fabricate devices. onsemi acquired GT Advanced Technologies to get access to internal substrates. And if you look at Soitec, it's manufacturing engineering samples. So anytime you have a very expensive way of making a substrate, very labor intensive way of making a substrate, there are going to be efforts to come up with disruptive substrate types of solutions. And Soitec is one of those efforts where they're looking at engineered substrates. Okay, another thing we need to take into consideration is that silicon carbide today is fabricated on 150 millimeter wafers. And as we're getting to 200 millimeter wafer commercial production, then assuming that the cost of the 200 millimeter wafer will be the same per centimeter square as the 150 millimeter wafer, we're looking at a cost reduction in fabrication, assuming same cost per centimeter square and same defect density or better for the 200 millimeter, we're looking at a reduction of 20% in cost. So that's another knob we can turn to reduce the cost of silicon carbide devices. Okay, so silicon carbide fabrication, of course, requires investment in specific tools and the development of specific non-CMOS compatible processes. So we've taken everything that's available from silicon and we've basically developed specific processes for fabricating silicon carbide that do not exist in silicon. And some of those are the way we do the etch. It has to be a dry etch and it's a hard material. So selection of masks and optimizing the conditions is a big thing. We have to thin the substrate because that's a big portion of the overall device resistance at the 600 to about 1700 volt range devices. When it comes to doping, we cannot do diffusion, thermal diffusion doping like is done in silicon. We have to do implantation. It has to be a heated implantation. So you need a tool, heated implanter that's specific to silicon carbide. Metallization, of course, you want to have CTE matched metals to the silicon carbide. Ohmic contact formation because of the big band gap of silicon carbide as well as GaN. If you put metal down on the silicon carbide wafer, you're going to get a Schottky. So you have to follow a process to create a low resistivity ohmic contact. The gate oxide, that's a big issue. The silicon carbide oxide interface is of rather poor quality. There are a lot of traps, and that basically compromises the device. It reduces the mobility, so high resistance, and it also creates threshold voltage instability, which can be a reliability concern. And then the silicon carbide wafers are, of course, transparent because of their band gap. So any silicon tools that use, optical beams, to do measurements like CD-SEMS, metrology, inspection, those will not work with silicon carbide wafers. So, of course, at this point, the silicon carbide market is large enough that there are offerings for silicon carbide transparent wafers by KLA and other equipment manufacturers. And then, silicon carbide wafers are not as flat as silicon, and that can have consequences when it comes to fabrication, particularly for higher voltage devices that have a thick epi. And of course, you have to use insulation dielectrics that, by default will contain some defects. So overall, you can process silicon carbide in a mature silicon fab. The critical dimension is about 0.3 microns. So even 180 nanometer fab, silicon fab will work. And you need to make an investment in specific tools for the silicon carbide processes like the high temperature annealer and the high temperature implanter. You need a tool to thin the substrate. Backside metal deposition, these are good metals that are compatible, CT compatible with silicon carbide. You can do an RTA for the ohmic contact or use a laser anneal tool that's specific to silicon carbide. And of course, you need inspection, tools to look at the epitaxy and the substrate. So for your metrology and inspection, overall speaking, you can go into a mature silicon fab and, with an investment in those tools and development of the processes, you're able to do silicon and silicon carbide fabrication at the same facility. So just to give you an example for heated implantation, this is the silicon carbide transparent quarter wafer before implantation. And this is after heated implantation. And you see that now it's become opaque, which means that you've turned the crystal into glass. And that's why you need to go in and do an anneal at 1600 to 1700 degrees to basically recrystallize the wafer, get back the crystallinity that was destroyed by the intense intense bombardment of the ion implant, and also activate the doping. So you need to put, an example of specific processes. You need to put a cap layer on the silicon carbide, and you can see here without a cap layer, the surface of the wafer gets destroyed. And when you put the cap layer, you get a very good surface in that processing step. Okay, so I just wanted to give some information on the silicon carbide, fab infrastructure. It does follow the model of silicon quite well. You have the IDMs, and in the United States, there's Wolfspeed, Microchip, GE, onsemi are some of the IDMs. You have pure play foundries like XFab that will take in fabless companies. There's a number of companies who are fabless or also go to XFab as a risk mitigation step. Companies like Microchip, Qorvo are some of the bigger ones. And of course, you have design houses that just do design and IP. And these are typically universities, and there are universities like NC State and SUNY and Sonrisa that have developed silicon carbide processes that are basically have been licensed by big companies to give them a head start in their silicon carbide fabrication. So we have a very robust silicon carbide fab infrastructure today that mirrors that of silicon, and that's very crucial in reducing, of course, fabrication cost, and particularly the model where you have silicon carbide fabricated in a silicon fab, because that allows you to fabricate silicon carbide in a high volume facility and basically exploit the economies, the fabrication economies of scale. Okay, so moving to some of the barriers to mass wide bandgap adoption for silicon carbide, of course, the high device cost is a big thing. Defect reliability and ruggedness concerns are still out there. And of course, the need to have an educated workforce that can fully exploit the properties of silicon carbide and GaN by putting them efficiently in circuits and systems. And that's more, of course, on the device level. And what we do at Power America is a member-driven consortium of industry universities and national labs. And our goal is to accelerate silicon carbide and GaN, power electronics. So all the way starting from fab and materials, we have several companies active in this area. Then we have companies that fabricate the devices into the circuits and the modules. And of course, we have a number of companies that take silicon carbide and GaN modules and insert them in systems to basically exploit the benefits, the efficiency benefits of those new materials. And we're affiliated with some of the best universities in the United States, working together with them to solve silicon carbide and GaN problems. And of course, we're affiliated with a number of US national labs. And over the past few years, we've spent basically more than $150 million in silicon carbide and GaN projects. And the goal is to overcome barriers and address, of course, all major technology areas. So over time, we've done 67 projects in device and fab, 28 projects in modules and reliability, GaN application and silicon carbide applications at lower voltage, and of course, higher voltage silicon carbide applications, so medium voltage applications using 10 kV silicon carbide devices. And we've done a lot of work in educating and training the workforce in wide bandgap devices and power electronics. So with respect to cost, this is an older graph, but it's still valid today. It shows that the cost of silicon devices is about 2 to 3 times lower than the cost of silicon. And of course, that differential gets a lot worse when you go to higher higher current capability, because the silicon carbide device, of course, has to be of a certain area in order to get good yields. Once you exceed this area, the defects can compromise your yields. And if you look at the PV, and this is information from Infineon, you can see that the silicon photovoltaic inverter, the semiconductor cost is 1/3 of the cost of the silicon carbide inverter. But the overall cost of the system for a silicon carbide inverter is lower. So the question is, you're paying 3 times more for the semiconductor compared to silicon. How come the silicon carbide cost is lower? And the answer is very, very simple. When you use silicon carbide or GaN for that matter, you're able to operate it efficiently at higher frequencies. And when you get to higher frequencies, you reduce the size of passive components like transformers and inductors and capacitors. They all become much smaller. So the overall cost of the system goes down. So basically for mass silicon carbide as well as GaN commercialization, if the cost savings at the system level, must outweigh the higher cost of silicon carbide devices. That is a reality in photovoltaic, and we're getting closer to that level when it comes to traction inverters for electric vehicles. So moving forward, let's see, I think there we go. Okay, so I'm going to close with some reliability and ruggedness concerns. You want to minimize, of course, material defects, improve the planarity of the wafer, Make sure you don't generate defects during processing, which happens at implantation. And of course, get a high quality gate oxide to reduce the threshold voltage instability. And those are requirements to get the devices accepted by the power electronics engineers. And of course, you got to have good short circuit performance and high avalanche energy tolerance, comparable to that of silicon. So the power electronics engineers can feel comfortable making the transition from silicon to silicon carbide. And of course, the education plays a big role. You want to be able to insert the silicon carbide devices and GaN that have very high DVDT, as Christina mentioned, and voltage overshoots. And it takes knowledge for the power electronics engineer to optimize those circuits, as well, of course, as the modules. And that is why that over our 6 years at Power America, we've trained more than 410 full-time students and engaged more than 4,000 people in tutorials, short courses, and webinars. Okay, so getting to the package to end my talk, Christina gave an excellent presentation on the issues. You want double-side cooling, of course, because these devices are capable of high power operation. You want to eliminate the wire bonds because they introduce inductance, and when you have those high DVDTs, inductance can be a real problem. You want to design the base plate, the heat sink for higher thermal conductivity, encapsulation materials, high voltage, high temperature. You need those materials optimized as well. And of course, the die attachment and thermal interface, everything that has to do with, the packaging in the module will not work from silicon. It will not allow you to get full performance benefits from silicon carbide. And that's why there's a lot of work done in the modules. And over the years at Power America, as I mentioned, we've done a lot of work in modules because that's one of the big gaps in silicon carbide technology. So General Electric, we funded 650 volts to 6.5 kV type of module work. And, the modules, low inductance, high temperature. And same thing with Wolfspeed. We funded work to do 1.7, 3.3, 6.5, and 10 kV modules, and also investigate the degradation mechanisms, numerous projects in this area. And of course, we funded a number of universities. This is Christina. She talked about her 10 kV work, double-side cooling for GaN and integration of the gate drive. And same thing here, looking at GaN modules and failure mechanisms, making power packaging technology compatible with commercialization, an effort by NC State, Transform, and USCI, both silicon carbide and GaN. And of course, this is another project by Christina where she does integration of the gate drives. She talked about that in her talk. And microchip with University of Arkansas. This project is very interesting, 1600 amps. That's a lot of devices to parallel. And of course, a lot of issues to get to that type of current level. So that's a very interesting project that we're performing at Power America. And this is double-side cooling for GaN with an integrated gate drive. University of Tennessee is driving this effort with GaN Systems and NREL. This is one of our latest projects. We're looking at current sharing between silicon carbide modules. That's crucial to get to the high current levels that are needed. And of course, there's another project here with NC State, NGE, and they're looking in paralleling GaN modules this time for high power applications. So a lot of work in GaN packaging, in GaN and silicon carbide packaging and modules from Power America. And with that, I would like to thank you for your attention and happy to answer any questions you might have.
Thank you, Victor. Impressive work again from Power America. Also a lot of work. We had one question, which was 200 millimeter silicon carbide was in 2015. What is now the possible size of silicon carbide?
Yeah, so 2015 was the demonstration. Between demonstration of a wafer and the actual commercial availability, it typically takes 7 to 8 years. So at this point, Wolfspeed does have 200 millimeter wafers that they're qualifying in a 200 millimeter fab. They are setting up in New York State. but those 200 millimeter wafers have not been made available commercially. So what will it take to get there? The cost is a big issue. If you look at the 150 millimeter wafers, they have a 350 micron thickness. The 200 millimeter wafers for stability have a 500 micron thickness. And of course, you know that the cost of silicon carbide is pretty high. So a lot of the effort is reducing the cost to at least make the 200 millimeter wafer cost the same per centimeter square as the 150 millimeter wafer, and the same thing with defects. So I would say that at the forefront of the 200 millimeter wafers is our Wolfspeed that's already processing them in a qualification stage, and 2.6. But there are a lot of engineering samples at 200 millimeters, and there are a lot of efforts in Europe as well as the United States to basically start processing 200 millimeter wafers and take care of some of the fabrication issues when it comes to this larger area wafer. Now, the last thing I want to say is that when you get to 200 millimeters, you'll be able to exploit newer, more capable tools. So certainly it's a step in the right direction, reduction of cost and basically better yields, because of the better tool quality.
Okay, thank you again, Victor, for this great presentation. The last speaker for today is Amin Aloush. He will, from Yole, he will talk about the reverse technology and cost for power device packaging. Amin, the floor is yours.
Thank you, Edgar. So do you see my screen?
Yeah, we can hear you very well.
Great. So welcome again to this last presentation of today. My name is Amin Aloush. I'm a technology and cost analyst at Yole System Plus, which is part of Yole group of companies. And I'll be giving you an overview about technology and cost for power devices packaging. So after a brief introduction, I will present different aspects of discrete power devices packaging, both on technological and a cost point of view. Then I'll continue with power module packaging aspect with some market figures and also technology and cost analysis. And I will illustrate that with some automotive and industrial power modules we have analyzed at Yole System Plus. So the context for today is the power electronics packaging. So as you all know, the packaging of a power device is a key element to have an efficient final device. So it is more than a simple shell. The packaging can really make or break a design. In the last years, we have observed different innovations on power devices packaging. For example, for power modules, these innovations are on different levels. For the cooling technique, the substrates of the power module, the die attach materials, and also the interconnection techniques. So all these innovations are targeting both industrial and also automotive applications, especially for the latter. The innovations are keen to support the vehicle electrification transition. So different requirements depending on the power level of the power application. So for example, for low power level applications, such as consumer application, compactness is a key element to consider, while for higher power levels, reliability and thermal management is an important requirement. So to redefine a bit what we will be talking about in this presentation, we present two components, two types of packaging. So we start from semiconductor chips that we need to assemble them inside either a discrete package or a power module package. So discrete component packages generally entail single die more often. They have reduced footprint compared to the power modules, which entails many dies and have larger footprint. So our methodology at Yole System Plus to analyze all these components is reverse costing that entails the tear down analysis first. So we open the device, we perform cross section in order to identify the manufacturing process flow. And then we simulate this process flow and we perform the costing analysis. So let's start by discrete power device packaging. So at Yole System Plus, we have covered almost different types of discrete packages, from the lowest footprint to the highest footprint packages. Each one of them is characterized by specific design choices. For example, interconnections. We have seen wire bonds, clips, or even ribbons. And for smaller, smallest footprint packages, such as chip size packages, there were not direct interconnection included. Other design aspects are die attach material choices, from tin-based solders to several field adhesives or other types of die attach materials. Also wire bond materials, aluminum, copper, but also gold material. So let's now take a closer look inside the package molding. So in this graph on the y-axis, we show the volume percentage of the total molded package volume. And we break it down in terms of the volume of each part inside, for example, the dies volume, wires volume, die attach, even the copper volume inside, which is coming from, for example, the lead frame or the copper clips, which is here represented in orange color in the graph. And for specific package, as you may see, we have an important amount of copper volume inside the discrete package, because these type of packages are employing dual side cooling discrete packaging. What is the cost impact now of all these technology parameters on the cost? We selected in this graph different discrete packages, and we break down the packaging cost in terms of its different parts. So for some packaging, we can see for the two first ones an important cost impact for consumable, for example, and this may be justified by specific choices of material, such as the gold employed in the wires, for example. So to sum up, for discrete package devices, we covered different aspects from the footprint, die attach materials, interconnection types. And for more details, you can check our Yole System Plus report about discrete power device packaging to have more detailed information about all these aspects. So for now, let's move to the power modules packaging. And as you all know, the power package or the power module market is really a dynamic market, and the promising one. It is, for example, expected to reach $10.5 billion by 2027. And it is a worldwide market with worldwide players, as you may see on this map, where we illustrated some of power modules that we have analyzed for some manufacturers. So at Yole System Plus, we really covered the analysis of plenty of power modules that allowed us to have a comprehensive view of the power module structure and to observe the different trends and the design solutions implemented in them. And to illustrate that, we have in this schematic a standard structure of the power module, and with the corresponding solutions proposed by different manufacturers, depending on the performances on the targeted applications as well. So for example, for case of the power module, we have seen molded case, plastic case as well, or even metallic case for the different attach for even dies or substrates. We have seen solders or even sintering technique used. For the base plates, there is some flat base plates or even more structured base plates like pin-fin base plates or an integrated pin-fin as well. For the substrates employed inside the power module, different solutions from dual bonded copper, active metal brazing substrates, IMS substrate, etc. And last but not least, for interconnection, different solutions as well, from a direct lead bonding or aluminum wire bonding, different kind of clips based on copper alloys, for example, silver clips, and even ribbon bonding employed. So different solutions. Some of these solutions have been observed in some automotive power modules. And here are few of them we have analyzed. So interconnections here vary from aluminum wire bond, clips, and copper alloys as spacers for the different players we have analyzed. For the automotive market and automotive application, we covered different power modules that we have analyzed, and we have extracted from different inverters and converters. These power modules are coming from different cars with different electrification level, from battery electric vehicles to fuel cell electric vehicle to hybrid electric vehicle. So we analyze the system in our teardown tracks, the inverters or the converters, in which also we analyze the power module inside. For example, wall speed inside the Lucid Air, the Hitachi power module inside the Audi e-tron or the Porsche Taycan, Vitesco Technologies power module inside the Jaguar I-Pace, Denso power modules inside Toyota Mirai 2, and the Toyota modules inside also the Toyota Prius. So if you get now a closer look to some of these automotive power modules, and we can start by the Hitachi power module that was found in the main inverter of the Audi e-tron, that is also present in the inverter of the Porsche Taycan. So as you can see on the image on the right, this power module entails an integrated heatsink here in the metallic case with its emitter plates and collector plates. Another example as well, we analyzed Vitesco Technologies power module inside the inverter of the Jaguar I-Pace. These power modules have very specific heatsink structure optimized for direct liquid cooling, as you may see. It also employs as interconnection clips with specific structure, also employs sintering technology as an attach. So what is the impact of all these technology parameters now from a cost point of view? To answer to this question, we chose to show you the example of power modules. First one is based on IGBT, silicon-based power module, and the two others are based on silicon carbide MOSFETs. Just to tell and to show that the chips and the dies have more important cost impact when it comes to silicon carbide technology on the overall module cost compared to IGBTs, for example, that have lower cost impact proportionally compared to the other silicon carbide power modules. And for the silicon based power module case, we can see that also the reduced cost impact of the chip allows a higher cost impact for the package itself with the bill of material proportionally to the other modules. So now I continue with other examples of power modules, but now for industrial applications. And as a first example, a Star Power 1200 volt silicon carbide MOSFET power module. This power module was an object of full reverse costing study we have already performed, like the other modules. It employs sintering technology and integrates a flat base plate, and it's targeting industrial applications. Another example of a power module we have analyzed is General Electric 1200 volt silicon carbide MOSFET, which integrates third generation silicon carbide MOSFET dies from General Electric, and it uses the power overlay technology as a packaging solution for the module. And here you can see on the bottom the optical view of the package cross-section we have performed internally in our laboratory, where we can see the different chips interconnected with the top copper layer corresponding to the power overlay structure. So in conclusion, power packaging market is a very promising market. We have seen different trends more and more. For cooling, there is a tendency for a double side and direct cooling. Tendency also for wire bond free solutions as a die attach, more sintering rather than the conventional soldering methodology. And for materials as well, we can see silicon nitride substrates, for example, inside the power modules compared to alumina substrates. And for more information, you can check our reports from Yole System Plus for the discrete power device packaging comparison, the automotive power module comparison, and last but not least, the General Electric 1200 volt silicon carbide module. So this brings my presentation to the end, and I want to thank you very much for your attention.
Thank you for this interesting presentation. I have to say we have quite a number of questions. So maybe the first one, what is the top 3 drivers for the bill of material reduction? You send the question?
Yes. To drive the cost down of the bill of material of power module, first, of course, the chips have an important impact if I talk about power module. And also the assembly itself, so the types and the materials you use for your base plates, for your substrate, it also have a cost impact, and also your interconnection choices, and the cooling technique if needed for your power module solution.
And then another question is about copper sintering. When will copper sintering, or when, maybe the first question is, when will sintering be in volume manufacturing, and then maybe copper?
Yes, for now, since we really start from already commercialized devices and power modules, we see more silver sintering now for volume manufacturing. Different players have chosen this solution to enhance the conduction performances. Copper sintering, of course, it's ongoing. Different players are on that, but we're still waiting for the volume manufacturing indeed. We hope that we can see it in the near future.
Maybe a question about, so your colleague Gabriela showed a lot about system in packages. Do you see a lot of the power technology like gallium nitride to also start playing a big role in that domain, or?
So system in package. So here I showed an example for example, General Electric power module. For power electronics, yes, system in package, what you can say is we can have maybe more integrated packaging designs where we integrate the chips. We can embed them inside specific structures like the General Electric solution with its power overlay. For sure, for gallium nitride, it would be one possible solution indeed to see more and more these integrated packaging solutions and more and more embedded chips inside the packaging design.
That's another question from Andrew Young. And he's asking, will gallium nitride challenge silicon carbide in the future? This is, I think, also an interesting question for that I had for Victor, because we see, of course, that gallium nitride has quite interesting performances.
Yes, I would say for gallium, each one is targeting application. So my feeling is the two solutions for now are cohabiting together. Each one is proposing performances at different power levels, for example, and also applications. So silicon carbide can be more confirmed solution and mature solution for some automotive applications, for example, but still for gallium nitride, they still need to be confirmed and qualified, and this indeed takes time.
And it means, so it means gallium nitride on gallium nitride. My apology. So
if I could step in here for just a second, if that's okay.
Please.
So the big advantage of the lateral GaN is that it's fully compatible with silicon. So you can fabricate it in large fabs like TSMC and basically exploit the economies of scale. Now, when you go to GaN on GaN, it's going to be a vertical device. It will allow you to operate beyond the 600, maybe 900 volt kind of sweet spot of lateral GaN. But one of the issues there is, of course, the very high mobility of lateral GaN is because of that inversion layer. now the mobility is going to come from the vertical conduction, which is not going to be as high as it is in the lateral inversion layer. The other issue is in order to fabricate vertical devices, so GaN on GaN to make the vertical device, the silicon processing, just like in this case of silicon carbide, is not sufficient. So you need to develop processes specific for vertical GaN fabrication, just like you're doing in silicon carbide, and you're going to need some specialized equipment, just like you need in silicon carbide. So the real question, because everything, of course, is driven by economics and numbers, is if you are to do vertical GaN on GaN and get to the 1200 volts, silicon carbide MOSFETs have been a product since 2011 at 1200, and there are a number of companies that have offerings in in silicon carbide. The question is, are you going to have enough of a performance improvement in your vertical GaN to successfully compete with a 1200 volt silicon carbide 1.7, 3.3? Because once you get to vertical GaN, you're able to go all the way out to 10 kV. Like you can make unipolar device out of 10 kV. So that remains to be seen. At this point, lateral GaN is, the sweet spot is at 600 volts. There are a ton of applications in that area: onboard chargers, conventional 400 volt electric vehicle traction inverters, and of course the massive consumer electronics market that GaN has. So in a way, today the different segments of the markets are being served by the different materials. And of course, GaN on GaN is not commercially available yet, as the question says. Next Gen in the United States, Odyssey in the United States, they're all working on vertical GaN, and it will be very interesting to see how that will compete with I would call mature silicon carbide, 900, 1200, and 1.7 kV solutions.